Okay, welcome everybody. My name is Jens Paulsberg. I am your moderator today and ask questions just like the first few days of the summer school. Today, our speaker is John Martinis. He started to work on experiments with superconducting qubits all the way back in the mid-80s when he was working on his PhD. And then he has continued to work on low temperature device physics throughout his career. And he has been doing quantum computation since the 90s. And he got the London Prize in low temperature physics in 2014. And that same year was the year when he also started to work at Google on building a useful quantum computer. And as we all know, it culminated with the quantum supremacy experiment that we all know about in 2019. He is from Berkeley. He got both his undergraduate degree and PhD from Berkeley, and has been a professor at UC Santa Barbara since 2004. And at the moment, he is in Australia. And so he is on Zoom today from a land down under, and he is the legend, John Martinis. Over to you.
Okay, thank you very much. I really appreciate the invitation to give this lecture. And I quite enjoy the subject. And I hope we'll have a useful lecture for you and different point of view. I think it's very important to be asking questions, and I'll be stopping my slide and getting them. And I think more questions, the better generally. If there's too much, because we have to keep a good pace, we'll move on and answer the more detailed questions at the end. But please give questions. In fact, as a professor, the questions are the most interesting part about the lecture, because then you understand what are maybe the sticky or subtle points, and that actually helps you understand the field better. So that's part of the reason I like to do these kind of lectures is to do that. So let's get started and share my screen. And okay, oops, what's going on here? Okay, there we go. It started on the wrong slide. So here we are in my first slide, just as an overview. And it's kind of an experimentalist view of the surface code and error correction, specifically the surface code. I'm going to give a review in the beginning, and what kind of reviewing the big concepts, and I probably a good time to do that, and as you can see here. And the concept here is, if you're going to build a quantum computer, it requires a huge team to do that, and you want to have a description of error correction that everyone can understand. All the engineers, for example, on your team, you can understand, and make sure that the physicists all understand it at a deep conceptual level, but also in a higher level that, just kind of easier. And maybe one way to say this, if you're doing this and you want to describe what's going on to your spouse, okay, I'm trying to give the easy enough concepts here that you can do that. But note, I'm saying spouse and not boyfriend and girlfriend, because I think describing the surface code to someone who's not committed to you is a little bit dangerous, okay? And I don't want, to ruin any relationships, okay? But, I think it'll be at a nice level where people can understand. Again, questions there is great. I'm also going to talk about how do you explain error correction to electrical engineers at kind of even at a higher level. It's interesting. Important slide is, what are the system specifications for error correction? And I hope that to be interesting. I know a lot of people are interested in improving error correction and inventing them. And I want to make sure people understand kind of the global things you have to worry about as an experimentalist. And it's nice. The surface code is an existence proof that things work well. You can build something. If you can make it better, that's great. You really have to understand the subtleties here. Then I'm going to go into the description of the data. And we'll first talk about the assumption of digitized errors, which is very fundamental to the whole description of surface codes. And although you expect this theoretically, I really want to explain why, experimentally, this assumption is looking very good. And I want to explain that. And then finally, I'm going to go to real experimental data on the surface code. There's a very nice paper put on the archive in February on a surface code-like experiment. I go through that very carefully, explain that, and talk about things. And things are looking really good for that, but there's still some challenges. So it'll be nice to end up with that. So let's get started. Okay. Okay. So to get started next, I need to go into, let's see, I need to escape this. I need to go into another slide presentation, which is given here. And there's present. Okay. Now, let's talk about very high level what we're doing. So physical qubits are error prone fundamentally, unlike classical information. And you have the T1, which is energy relaxation, and a T2 is kind of what the phase noise is doing. And when you build these quantum gates from physical devices, they have 10 to the minus 2, maybe 10 to the minus 4 errors, okay? And we're gonna be building, wanting to run algorithms in software that has, let's say, 10 to the 20 operations in total, maybe less, maybe more. But it's kind of like classical algorithms where you have a huge number of gates. And that means you have to have very low errors. And unlike classical information, which intrinsically has low error rates, maybe of order 10 to the minus 20, sometimes not, but it's always low, okay? How do you make that up? And of course, you do that with error correction. And that's gonna take a lot of physical qubits per logical qubits to do that, okay? So let's understand that, and as you've been understanding that here. So let's just start with just a very simple idea of why this is so hard in quantum mechanics. So we start with classical information, and I like to think very conceptually as a coin on a table. And you put a coin on your table, it's either heads or tails, and that's a stable piece of classical information. And it's stable is because there's a restoring force for the coin to lift off the table. And there's also dissipation to that restoring force so that it will relax to heads or tails, given, let's say it's given more energy. Throw a coin on a table, it will relax to one or the other, and it will stay there, okay? And that, of course, makes classical information much more easy to operate on and the like, and because you can build it in a stable way. Now, in quantum bits, you can use the analogy of the coin, and you can think of the direction of the coin as the block vector, okay? And because there's no preferred orientation to the block vector, you can think of in this analogy as a coin in space, for example. And now you have any small force on that is going to rotate the coin in either around or flipping heads and tails, and you're going to get rotation errors from any small force. And thus there's no stabilizing effect on that, and it's going to be intrinsically have errors. And of course, we have to worry about that at the fundamental level. Now, when you go into quantum bit physics, of course, your quantum state is given by an amplitude and phase, as you see in the formula right here. And these amplitude and phases can be mapped to the two angular coordinates of the coin, okay? And then if you start thinking about, well, how do I stabilize that or measure if there's been any noise onto the device? The problem is if you want to say, for example, measure the amplitude of it, we know from quantum physics that fundamentally will randomize the phase. So if getting amplitude information, you mess up the phase information, and the vice versa. If you get phase information, that's going to feed back from the measurement and mess up the amplitude. And of course, when you think about that at this fundamental level, it looks very hopeless as to what you can do something. But what, of course, was invented, this is a just brilliant invention in the early 1990s, is you can do error correction. And it basically comes about, thinking about qubits, that if you measure 2 qubits, it's 2 coins, for example, you can measure the amplitude and phase parity at the same time. So the parity, of course, is at 0, 0, or 1, 1, gives you 1 parity, and 0, 1, and 1, 0 gives you another parity. And because of that, it's, you can do error correction by building the system. And so that's what I want to explain next. Okay, so the nice thing about this is it's not too hard to understand how the parity works. And then this would be the hardest part to explain to your spouse, but okay, you can be done. And we know in quantum measurement theory that whether the amplitude, measuring the amplitude will mess up the phase or vice versa, depends on the commutation relationship between the amplitude and phase. And for in the amplitude phase, the operators for a bit flip is sigma x operator, which turns a 0 into a 1, and the z operator turns a 1 into a -1. So this flips the bit and flips the phase. And with these basic operators, you can then figure out what happens when you do measure if there's been a bit flip or a phase flip. And you use the commutation relations xz minus zx. And that's not equal to 0, and that's why you have this fundamental issue. Now let's go ahead and do the mathematics right here for the 0 to 1 state. Let's do x, which turns 0 to 1, the 1 to 0. And now let's do a phase flip, and the 1 gets a minus sign in front of it, okay? And now let's do the opposite for the commutation. 0, 1, let's do a z, and that's 0 minus 1. There's a minus sign here, and then flips the bits, and it's 1 minus 0. And you see here that they're different answers. So xz does not equal to zx. But what's amazing, and this is, saves us as quantum physicists building a quantum computer, is in fact, it doesn't commute, but it anti-commutes. There's just a minus sign between this answer here and this answer here. Again, this was seen in quantum mechanics. You've seen that. So xz plus zx is equal to 0, or xz is minus zx. Okay. So how do you use that? I mean, this is something, since it's just a minus sign, okay, and of course, classically, there's no such thing as a minus sign in the amplitude, but quantum mechanically, that has a real effect. Okay, so you worry about that. However, let's talk about doing this with 2 qubits now. And we talk about now in x12, which is a bit flip on 2 of your qubits, and a phase flip, which is a phase z12, which is a phase flip on q1 and q2. So let's just do the commutation relationship of these two. So x1, x2, z1, z2, minus z1, z2, x1, x2. The 1s and 2s commute, they're different qubits, but then you can reorder this and you pick up a minus sign for each of the reorders, right? And because of the amazing mathematics that minus times minus equals plus 1, okay? 2 qubits gives you a cancellation. This is the same thing on the left side and right side, and it's a 0, okay? And again, knowing quantum mechanics, we know that if it commutes, these parity is operating kind of classical-like. You can measure the parity of 1 qubit without affecting the 1 pair, without measuring the x, without affecting the phase parity of the pair, okay? The important concept here is it turns it into a classical-like object, the parities. And what happens is when you go ahead and build your error correction, at least in conventional qubits, this is classical-like manipulation of information, and you can use classical codes and classical logic and all these things we have huge amount of information on to go ahead and design and build your error correction code. And this is very important. And then it's kind of a mathematical classical operation, and you do that. And that's why I'm sure, as you've been learning, you can use a lot of classical concepts from classical error correction to solve and imagine what you're going to do here. Okay, and that, I think, to me, that's the most amazing thing about all this, is this simple idea of parity gets you into a mathematical framework that you can deal with, especially if you're dealing with it in a very complex manner, as you do in quantum mechanics.
So maybe I can ask you, John, what if the phase gets messed up more than just plus to minus, but instead it goes from plus to something weird?
Okay, so this has to do with the digitization of errors, which I will talk about a little bit later. And this is actually one of the fundamental assumptions you make here, okay, is that you can have a small change in phase or small change in amplitude, and you can digitize that as either no error at all with some probability, or a small probability, for example, that you had a full bit flip. And that is not an obvious assumption, and we'll talk about that. But for right now, that's the way we're going to talk about. That's the way it has been talked about, and I will get to that because, frankly, that's the most amazing thing about quantum mechanics. And mostly, I'm going to talk about that, but I have a whole section of my talk to experimentally test that idea, because that is one of the most amazing ideas in quantum mechanics, that you can do that, and I'll get to it. Okay, now let's talk about step 3. The parities behave classically. So that means in quantum language, it's a simultaneous eigenstates. But what it basically means is when you measure parity, bit and phase parity, you're going to get the same answer and over again. Okay, so let's just do a simple experiment on 2 qubits. You measure the Z12, okay, and let's say you get a +1, and then you measure X12, and then you get a -1, okay, for the parity. And then you measure Z12 again. And because these commute, Z12 should be +1, because they commute and one didn't mess up the other, X12 -1. Same thing again. Now, if your qubits were perfect, you would measure that parity. Of course, you don't know the state of the individual state inside that, but you can measure the parity and get that information. But let's say, for example, the Z12 had a +1, and then you measure the parity of -1 at this point right here, then you know there is an error in your system. And this is the digitization of errors that we question was about. I'll explain it some more later. So you know there is an error. Okay, now note that there is an error here. If you measure X12 again, because they commute, it's going to be a -1. You're okay there, but you're going to have an error. Okay, so you know you can detect an error, whereas not, let's say, screwing up the other parity measurement. Now, of course, the problem is you want to know, okay, there is an error. How can I correct for that error? The problem is you don't know whether it came from qubit 1 or qubit 2. Okay, so that's what error correction is about, is encoding it in a more complex way to figure out where it came from. So what I'm going to do here is talk about 3 qubits that are connected with measurements along a line. And this is what we'll talk about experimentally at the end of the talk. And then we're going to measure the parity of 1, 2 through a Z12 and Z23. And this is a classical analogy. Let's just say we're just going to measure Z's and not X's, but you can see what's going on by just this simple classical. So Z12 measures the parity, whether this is a 0, 1 and 0, 1 in parity sense. So let's say you just look at all the states. You look at 0, 0, 0. And the parity is going to be 0 and 0 here between that. Sorry, I've changed from +1 and -1 to 0 and 1, but you can understand that. If it's 1, 0, 1, the parity of these are 1, then the parity is these two, it's the same as 0. And you can move across here, that's 1, 1, and then through 0, 0, 1, it's 0 and 0 and 1. Okay, and you can see that if you were in any one of these states here, and then you had a single bit flip, or let's say you had the 0, 0, 0 state. Let's say you started with that, you're measuring a parity 0, 0, and you had a bit flip, 0 goes to 1 somewhere. It's going to go, you don't know which qubit, but you're going to do the measurement here, and from either a 1, 0 or a 1, 1 or 0, 1, you can figure out which one flipped. So called repetition code, you can tell if things flipped, you could then unflip it, for example, if you wanted to put a gate on that. So it's unique decoding for a single error. The problem is, what happens if you have more than one error? So let's say these two bits flip to 0, 1, 1. Now you do the parity, and you're going to get a 1 between these two. These two are the same. That's going to be a 0. And now you see the measurement to the parity 1, 0 is the same as this. So if you're going to use this detection table, then you're going to flip this bit, and you're going to go to 1, 1, 1. Okay. And in fact, you see that the errors, and that's going to be an error in your decoding scheme. Okay. And you see when you have an error, you actually flip all the bits, it turns out. Okay. And you say flip 3 bits, you're going to get a 0, 0, and you think that everything's okay, but it's a 1, 1, 1. So what happens is, and this is a very important concept, is when you use this kind of parity error correction, you get a unique decoding if the error is small enough. Okay, if there's too many errors in there, you're gonna get faked out, and you're gonna decode and correct in the same way, and then you're gonna get an error. Now you see, this is an example with 3 qubits. I hope people can see that there's a way to solve this problem. Okay, this is a fundamental problem. And that is you add more and more bits. I guess I'm talking classically here. You put 4 or 5 or 6 qubits. And then as you add more bits, then you could have more correlated errors, that's the wrong word, more double or triple errors in a cycle. And then you can decode it properly. So that's because if you assume independent errors of all the qubits, the chance of getting many errors at the same time goes down. And in fact, if you think about classical probability, just go back to your high school statistics course, the classical probability of all of them flipping is going to be very small. You throw 10 coins on a table, what's the chance of them all being heads? Okay, that's very small. It gets exponentially small. So in fact, the errors get exponentially small as you build it bigger and bigger. And this is the basic reason why you need so many qubits to build the surface code. You need 30 or so in terms of a bit flip parity to make sure that, if you flip 15 or less, it's okay. So for flipping 16 is really unlikely. And then you need another 30 or so for the phase flip. And then these two numbers actually multiply. That's why you have so many qubits needed, at least in the surface code. And that's generally why you need it. Now, if you had errors in qubits that were 10 to the -10, you don't need very many qubits. Okay, it's a competition between the errors. And the problem is that the errors in qubits are quite high. And you know what, we've been doing this seriously for 20 years now, and I've been working on it more than 30 years. And right now, if you build a big system, the typical error rates are about 1% or 2%. Heroic devices, well-designed devices get you down to 0.5%. Now, I think that's going to improve over time, but I hope you understand that it's taken a long time to get here. So the chance of a 10 to the minus 5 or 10 to the minus 10 physical qubit is pretty low. Okay, so you should be assuming right now, because that's what nature has told us in 20, 30 years of doing experiments, that it's pretty hard to get error rates because it's fundamentally hard, as I've talked about. Okay, so
question for you, John. So just going up to the top part of the slides, what's the purpose of showing these ZZ and XX measurements interleaved? Could you do the same with multiple ZZ measurements all across?
Yeah, and in fact, what I'm trying to do, thank you. I'm concluding in this section, so it's a good time to break here. I'm showing just simple parities because that's easy to understand and you can get the concept of what's going on. Now, it turns out, because it's just based on parity, you can do more complex parities. And that's what I'll talk about in the surface code of, for example, parity of 4 qubits. And if you look at the full range of all possible things, you see it can be much more complicated than that. So people have done that. But I want to make sure that people understand that the parity concept and the simultaneous eigenstate concept is very fundamental of how builds everything. And the classicalness of these commuting eigenstates is absolutely essential for turning this into a classical problem, because here I've really given you a classical description of what's going on, and because they commute. And of course, there's a rich field out there how to do that. This is the simplest example.
Z12, is that a stabilizer?
Yes, that's what we call the stabilizers.
Very good.
I'm sorry, I'm using a different language, and I'm trying to get the concept across instead of introducing jargon. Okay, so if you want to explain this to computer scientists and hardware engineers, we do that. But I like to think, in the end, these stabilizers are just these parity measurements and more complex parity measurements that commute with each other so that all of these measurements are classical-like. Okay, that's the concept here.
And one more. So when we talk about measuring parity, like again, this Z12 we just talked about, are we really talking about calculating 2-point correlation functions of a Z1 and a Z2? Because it's clear how the parity checks works for classical states, but what's going on when you're dealing with arbitrary superposition states?
Yeah, and that's going to be the next slide when I talk about the full surface code. So I'm introducing here the important concept of parity. And given that the codes are classical-like, then I can describe what's going on there. And then in the next slide, we'll talk about what goes on in the surface code, which is more complex than what we're seeing here. But I really want to get the idea that this parity concept, whenever I listen to long lectures about error correction, these concepts are assumed. But for me, these are like really subtle concepts that you need to understand fundamentally. And all I've done here is go down this very quickly, very carefully, so that people understand that this is the basis of how error correction works. Okay, and in some sense, it's so simple that it's usually, driven over really fast in a description. And I just want people to understand how important this is and to know, what you're extracting doing these parity measurements. Okay, thank you for the questions. This is really important. Again, this is so simple. is typically just not talked about. But I'm trying to give an example, really pull out the information. And in some sense, how to turn this into a classical kind of concept it really comes from this. Good.
Just one more clarification about the truth table down here. Are these parity measurements for both Z12 and for X12, or what do you have in mind there?
Yes, they're parity measurements of 2 qubits, doing a measurement in the Z basis, say first, and then doing a measurement of the parity in the X basis. And I'll explain in the next slide. I'll show you how to do that. Okay, you know, this is you know, the basic idea.
Okay, so apparently the next page is very important, but before we get there, on the previous page, you use this notation with square brackets and some stuff, comma, some stuff. Where third to the last line. Could you just please go over that one more time, what the notation means?
So this is the commutation relationship that you learn in a quantum mechanics course. And bracket XZ is defined. So this should be a defined symbol, not an equal symbol, of X times Z minus Z times X. And it basically is discussing what happens if you reverse the order. Because in quantum mechanics, if you reverse the order of these operators, and again, I did the example of a measurement, then it's different. And that kind of, in some sense, describes the essence of the quantum mechanics of this. And this is what you learn in your quantum physics courses. And again, it's that. But you know, physically, think about, you take a tennis ball, and you draw a 0 at the North Pole and 1 at the South Pole, and then you do a bit flip. You rotate it 180 degrees around the equator, and then you rotate it 180 degrees around the poles. Okay, classically, when you do that, you get you get a different state, but it's the same whether you do one rotation first and the other rotation. In quantum mechanically, the amplitude changes by a minus sign, okay? And that has profoundly, you know, that completely changes everything. And again, when you do quantum mechanics experiment, that minus sign gives you that. It means you can't measure one or the other. But if you take 2 balls and you create this combined state, then it does a classical kind of rotation. Okay, and again, this is very mathematically and abstract. It's hard to explain that, but that's what happens with quantum mechanics. Okay. Okay. Great. Okay, so with this basis on how important parity is, we're now going to talk to the surface code. Okay, and we'll talk about how that works. And you know, there's a long, I've given a history, this is a history as of 5 or 7 years ago. There's a lot of basic physics here describing that. When I was introduced to the surface code, you know, reading these papers were like reading string theory papers. I couldn't understand anything. So it was very nice, really led by Austin Fowler, who talked yesterday, and then written mostly by Andrew Cleland. We wrote a paper which we hoped was friendly to, let's say, a graduate student level understanding of quantum mechanics. I mean, it's still hard. And we've gone through the whole description there. And actually, we're very proud of that paper because there's nothing really new in that paper, but because I think it's fairly clearly described, it has gotten a lot of citations and been very well read. And so, you know, I say this because I want to motivate people. Distilling complex theories into something that we can all understand is an important part of science, okay? And I would say what happened when we did this again, thanks to Austin and Andrew Cleland and Matteo, I then knew how to build a quantum computer, and it completely changed the experimental landscape for me. Okay, so this is the surface code. Now, if you just take one line of this, just this line right here, and forget about the Z's up in here, what each of these Z's means is that this particular, okay, so the open symbols are the data qubits, and the closed dots here are the measure qubits, which is going to be this parity measurement that I talked about. It. You measure it through a qubit, okay? And the data qubits is where we're storing the quantum data, and the measure qubits are where we're measuring these parities. Now, you see, for example, in this, you're measuring Z, okay? And Z is a bit parity, whether it's 0 or 1. And the orange is where you're doing the phase, which is measuring, basically whether it's 0 + 1 or 0 - 1 in the basis. Okay, so it's the two there. Now, if you take just this row right here, and let's forget about the connections down to here and here, this is measuring a Z1, Z2 between qubit 1 and 2. So this particular row right here, forgetting about the other rows, is exactly what we were talking about in the last slide. It's measuring, in essence, this parity, the 0-1 parity, the bit parity through a Z1, Z2. Now, these kind of measurements give you the bit flip. And then the same kind of thing can be thought about in this column right here, where between these qubits here, we have X and X, and that's now measuring the phase flip, the phase parity. And again, forgetting about the other columns, we're doing the same thing here. So you see, the generalization to a surface code is really connected to what I talked about in last time, but now we're doing it in 2 dimensions. One dimension is bit and one dimension is phase. Okay, and that's why it's essentially why it's a 2-dimensional grid of qubits. Okay, and then we have a lot of qubits in this direction to make sure that we can correct the errors to a large degree. And we have a lot of qubits in this direction, again, to correct the phase. I'm going to show why the particular arrangements of this, but note now, instead of being just Z1 and Z2, you now do a parity between 4 qubits. So that if it's 0, 0, 0, 0, it'll be 1 parity. And if it's 0, 0, 0, 1, it'll be another parity. But if it's 0, 1, 1, 0, where there's 2, then it'll go back to the same parity as 0. It's just a 4-qubit parity, but it's still looking for parities. Okay. Now, in terms of how to actually measure this is what I talk about down here. So we have a measure qubit looking at 4 data qubits around here. And versus time, this is what happens, is you initially start the measurement qubit in the ground state. You do nothing. And then you do a C0 operations with all the neighboring qubits. And then in the end, you do a measurement. Now, if you think about the C0 and how it operates, and you do a C0 on the 4 different qubits, that gives you a parity measurement, as I was just talking about. Because every time there's a 1 here, it flips this. So if it's all zeros, this will come out as 0. If there's one state in all of these, it'll flip it once. But if there's 2 1 states here, it'll flip 0 to 1, 1 to 0, and you'll go back to the 0 parity measurement. So you can kind of see, from the construction, you're getting a Z parity. Okay. And then in the oranges, you're now measuring the phase parity given here. And it turns out that to measure the phase parity, you have to introduce a Hadamard gate here, which turns a 0 and 1 into a plus or minus state. And then you reverse the C naughts in terms of the target. And I'm not going to go through and explain why that gives the phase parity. I guess that should have been or was a homework problem. And you can see that. I'll actually talk about this later, the right way to see this. But this gives a phase parity. And Hadamard, you do the measurement in the same way. Okay. And what we do in the surface code is we just repeatedly do these parity measurements. And then from the parity measurements, we can, because these commute, and I have to show that, but because of that, we get this classical information, and then we can figure out where the errors are. Okay, that's the magic. I'll show you that in the next slide. I'm just saying what you do right here. And now I'll explain in the next slide why this works. It's really kind of amazing invention by Bravi and Kaitera, the Torah code, you know, how this works. It's really cool. So any questions on this?
Would it be redundant to do parity checks in the Y direction?
So in some sense, let's say you're doing parity checks in Z, but you're also doing parity checks in the Y direction too. So you're actually doing it in two directions. And I'll explain, you know, kind of doing that. So you're really doing that too. But it's kind of interesting. Note you have to go from 1D to 2D to do both X and Z, and then it has to be constructed in a careful way.
Okay, another question.
I'll explain. It's a good question. I think I don't know how to answer it better than that, other than to show you more of how it works.
Does the measure on the measurement qubit change or collapse the state of the data qubit because now they're entangled because of C naught?
Yes, absolutely. And it collapses it to the eigenstates that I talked about previously. So for example, you have a complex state between the two qubits and you do a Z1 or 2, it collapses it in E to a parity +1 or -1. So it definitely does that. But what happens is these states right here, it turns out you can encode this information in a way so that you can encode a general state to it. And I'll explain that next. These are good questions because they're leading into the next slides. Okay, this is very good. I like it.
How often do you check the parity of these measure qubits?
So basically, the error correction is a parity checking machine. And, you know, 99% of what's happening is you're checking the parity and seeing if there's an error. So for example, in the experiment I'll show you, the basic gates here are about 20 nanoseconds. The measurement is about, I think, 880 nanoseconds. That's really slow. But, you know, you're doing that so that you're checking the parity every microsecond or so. And, you know, the qubit coherences are in the experiments about 20 microseconds. So you're checking it, you know, as often as you can with respect to the coherences. And of course, if it decoheres too fast, then it's not going to work because you're not checking it often enough. But the whole idea is you check it all the time because those qubits are wanting to decay, they're wanting to dephase. You know, just check it as fast as you can in order to prevent that from happening. And that's really important to understand. Now, you're going to have to do logic operations on top of that, and I'll get to that. Good question.
What about the poor qubits out on the edge? Are they going to, they're less connected than the other ones. Is that going to matter to the error correction of those?
I'll show that in a second. And you know, there are, at the edges, The errors at the edges you can correct for, but you have to kind of understand that more carefully. I'll get to that. That's a good question. Next slide and following slides, there are some boundary qubits, and they act a little bit differently.
Using
Okay.
surface code, is our state coded as a CAD state or as some other state?
It's encoded in a way that's kind of complex, okay? And so yes, this is a very good question, because when I was thinking about understanding the surface codes, I asked the same question to Austin over and over again. And it turns out that thinking about what the state is really hard to understand what's going on. If you had a few qubits, you can do that. It's more important to think about what happens if you apply a bit or phase flip to your state, and or how to change a state. Because what you do is you start out with the state where you know what the parities are, and then and you measure them and set the state. You make that a logical 0 or 1, and then you do logical operations to change that state. And you don't really care what's going on internally, because the logical state is distributed over many qubits, and actually writing down that state is not useful. But understanding what happens to a bit flip or phase flip can tell you what's going on. It's kind of going from a Schrodinger picture to a Heisenberg picture. Instead of talking about the wave function, you say, well, how does the wave function change by these operators? And unfortunately, except for very simple situations, you kind of have to get used to that language. And that's the language I'll be using. It'll be more clear as I go through and I use that language. But once I understood that, then how these things operate. And it just requires a more sophisticated understanding. So yes, this is why you can only explain this to your spouse. This is really hard. Okay.
So we have the diagram in front of us here. Is this telling us that surface codes are for quantum computers with a grid-like pattern and not an arbitrary pattern?
That's right. So it's this grid pattern, and but this is the important thing. You only have to connect the various measure and data qubits to its nearest neighbor. There's only 4 connections. Now, when you look at other coding, that's generally more complex and more qubits, okay? And the reason why, when I understood this thing, is when you talk about a 2D grid connecting to nearest neighbors, that's something you can build on a chip. And that's simple. And this is, in fact, the reason why I got so excited about the surface code when I heard about it, is that that's something you can build on a chip. And it turns out experimentally, if you have to connect a qubit to 8 or 10 other qubits that are far away, that's really hard quantum mechanically. Classically, you can send that information and copy it and do whatever you want. But all these qubits are interacting with each other in a quantum way, and having a simple architecture, in my view, makes it buildable. Now, okay, we'll see what happens in 20 years, but we know how to build it right now. And once I understood this, I then could see in the 20 years ahead what we would have to build and what we would have to get to work. This is buildable. Okay, this is in fact the most important thing about the surface code. Small connectivity, only 4 qubits, and a grid, a chip. You can build that on a chip.
In the example, again, back to the picture here in front of us, how many logical qubits are we talking about here? And can you talk about sort of how many logical and how many other qubits are there?
Yeah, so there's 1 logical qubits. Okay, and that's the next slide. That's a good question. Next slide. Okay.
Okay, so then moving on to the picture below, over to the right, we have this psi of z plus, z minus, psi, x plus, x minus. What is that?
Yeah, and that's the description, as it was asked previously. If the if the measurement qubit has a +1, so it's a even parity, then you collapse the state into an even parity state. And if it's an odd parity, you collapse the state into an odd parity state. So this is, what we were talking about before. And it's just saying that that kind of state collapse is going on. And in fact, it's kind of, you're doing the digitization of errors. Okay, that statement is really saying you're digitizing errors. And again, I'll get to that because that's a very important.
One more about this diagram. So it's clear that in one diagram for bit parity, you have C-naughts going in one direction, and the other for phase parity, you have the C-naughts going in the other direction. I think people want to know that this is not a typo.
No, this is absolutely correct. You see these other these Hadamard gates. Okay, so let me give you the homework problem right now. I'm going to use it later. This is the homework problem. From the top one, as you know what C0 does, you can see how that gives you parity. Okay, so that's great. Now, to understand how to get to the bottom one, I mean, you can just go through it, and this is complicated. But what you want to do is instead, there's this relation that says that a C0 can be made equivalent to a controlled Z, where you put Hadamards on the little plus signal and the like. So do a transformation of the top one to a control Z 2-qubit gate. And when you do that, you'll get some diagram on the top, okay? But on the bottom, you will get exactly the same CZs, except there are now Hadamards on all the qubits, okay? And the nice thing on the Hadamards and the qubit is that's equivalent to going, instead of measuring it in the bit amplitude basis, you're measuring it in the phase basis. And then there's a symmetry between the two that you fundamentally see, okay? But you have to go into the CZ basis. The bit is easier to see the parity, but the CZ, I think, is more fundamental because you see the symmetry between the two, and you're just going from an X to a Z basis, which is a phase or amplitude. So please do that homework problem. Okay, very simple. Just convert those C0s into CZs with Hadamard, and you'll see that.
Okay. Just a high-level question here. Does the Sycamore chip or any Rigetti chip or the like have enough qubits to make the surface code practical right now? And either way, is the surface code more suited for one kind of quantum computer than another one?
In terms, we'll talk about the chips later. But if you think about the Sycamore chip for the quantum supremacy experiment, it was this thing. And what the whole design of the Sycamore chip and the quantum supremacy was a stepping stone to doing error correction. So you'll see the results of the latest things. And this is what the group wants to do next, is to start doing the full surface code experiments. And we'll talk about that at the end. I don't know about the Rigetti chip, but let me discuss the IBM chip. The IBM chip has an architecture more like a honeycomb. And when you have one measure qubit, say, connected to 3 data qubits, it's not the surface code. And my understanding is that that will not allow you to do a scalable, efficient, proper stabilization of the qubit states. 3 connections are not enough. You need to have 4 connections to be able to do proper error correction. So, 3 is hard. IBM's working on it. I'm sure they're thinking about how to do it. But in the end, you need to go to this, you need to go to a 4-connection architecture. So it's very interesting. I'm not going to say that this is a hard theoretical proof, but it seems that if you want to do proper error correction, you need at least 4 connections for at least some of your qubits to get that to work. Okay, and that, again, that's more of a question for the theorists, but that's what my understanding is. So in some sense, if you think about the connectivity, this is the minimum architecture you would use in order to build it. Other codes have more parities and they're long distance. And, you know, maybe we can do that eventually, or maybe you do that with ion traps and that's fine. But, you know, if you just want to get the minimal state. And one of the idea of making it minimal is that your threshold for doing error correction will be better. And I'll come to that.
So we're looking at this picture of one logical qubit here, but where is the phase of that logical qubit if all these measurements keep collapsing the data qubit?
Well, let me get to the next slide. Okay, these are great questions, and you know, and let me, yeah, these are, yeah, they're great. The same questions I had when I learned about this. Okay, okay, so I think it's time to go on to the next slide. Okay, so oh, wrong way. Okay. So here's the surface code. And the first thing I want to do is talk about all the parity measurements and that they commute, right? So you want the measurements to be classical. And, you know, as I showed you before. And the interesting thing about these particular 4-qubit parities is they all commute. Okay, so let's go through that. Let's take these X's and these Z's. Okay, these X's, all X's commute with each other. So this measurement computes with this one, commutes to the neighbor because XX's commute. It's only between X and Z's. Now, if it's between this measurement, this stabilizer here, this measure qubit, and this one over here, they're different qubits. So of course they commute. Okay, it's only when they're neighboring each other that you have to worry about it. But when you look at a neighbor each other, there's always a pair of qubits that are connected between these two measuring and stabilizers. And because it's a pair, then it commutes in the way that I talked about before. So you can see that between all the neighbors, it does that. It's also true of the neighbors at the edges. Okay, it's also terms of the edge qubits and these things. So you can see it's everywhere that happens. Okay, so it's been constructed with these more generalized parity measurements to do that. Now, I want to mention one thing here. I believe there are 41 data qubits here and 40 measurement qubits here. And it's kind of the difference between these two. There's an extra data going over the measurement. So when you do the state collapse over measurement, you're not completely collapsing the state. There's still 1 qubit quantum left. And that's how your quantum state gets encoded. Okay. And now it's not obvious in detail how that works. I'll explain that later. But you're not measuring too much here, okay? Because if you were to measure 41, you know, these parities, you would collapse the whole state. But there's still a degree of freedom left, okay? And that's your logical state. Okay, now, all the measurements of the parities, XXXX, ZZ commute. And that means when you measure these, as I talked about last time, the measurement outcomes are going to be unchanging if there are no errors, right? So you're whatever it is, you measure it the first time and you collapse it into some state, and we'll talk about how to do that later. All those measurements outcomes will be unchanging because they all commute, just like I showed in the 2-qubit example. Okay, that's an important concept, critical concept. These are classical-like quantities of it. It remains unchanged. They don't affect each other. Okay. And then when you have an error in, you say, a data qubit, they tend to be pairs in space, although not always, and we'll talk about that later. But just say, pure data error. And when you have a measurement errors, it's pairs in time. This is important that it's pairs. So let's talk about that.
Well, let me interject a bit here. So why do measurements on different qubits commute if they are entangled?
They commute, well, because like I say, you just do the commutation relationship between XX and ZZs. And since it's always pairs, then they commute. It's a mathematical statement. And then what happens is you will collapse the state so that next time you measure it, it will still commute. So this really goes back, again, to this simple example, which is, these are great questions, okay? It goes back to this simple, whatever the state it was on, you projected it into an eigenstate where it was +1, and whatever the XZs was happening, you projected it to a -1. If you did the experiment again, this could be -1 and -1. It could be different numbers. But when you do the measurement, you project that. And because these are simultaneous eigenstates, they commute. It doesn't change with time.
And a very basic question, the terminology is always measure X, but what people know about is how to measure state. What does it mean when you say measure X?
Well, when you measure X, you measure, when you measure Z, measuring Z is saying you measure the 0, 1 of-ness of the multiple experiments, if it's 0 or if it's 1. And when you measure X, you measure in the phase direction, so whether it's a plus state or minus state. How much is it into the 1 and 0 and 0, 1? Now it's easy, we understand what's going on with one qubit here. And then what we're saying here is that you can generalize that to parities, to multiple qubits. And measuring the 0 or 1-ness is done with the C0. And then you can just do that multiple times and multiple qubits to get the total parity.
Very good. And then now that you have the picture in front of us here, there was this statement about there's this 1 degree of freedom left. Could you please repeat?
I will get to that in the next slide.
Awesome.
I'm previewing it, and I'm glad people are catching, because this is very beautiful how this works. Okay, so what's funny is we have to first talk about the errors and then talk about the state. Okay, it's kind of backwards. That's the way you have to think about it. Again, it took me a long time to understand. So anyway, we'll get to that. Great questions. Okay, so when you have an error, it occurs on. So let's talk about that. Let's say we had one of the data qubits. It flipped its state, 0 into 1, or 1 went to 0. Okay. Then when you measure that 0-1 parity, the bit parity with actually this was actually a phase flip because it's X. So it flipped from a plus to minus. So you had a phase flip on one of the qubits. Okay. Then when you measure the phase parity here, all these other ones are the same, but this one's different. And whatever parity it was in the last cycle now changed in one of the cycles, okay? And the same thing happens for this measurement. These guys didn't change, this guy changed, so you had an error here, okay? So if you change, in this case, a phase flip, but it could have been a bit flip in this direction, this way. So this qubit is protected for bit flips in this direction and phase flips for this direction. And if you had a phase flip, you detect it in the neighboring pairs, okay? And now you know where it is, right? You say, hey, there's a pair here and here. Where could it be? It's obviously in the center there. Or if it was a bit flip, you would get an error here, and it would be in the center there. So if there's if over time you keep track of what you were measuring for the bit and phase parities on all these qubits, on the measured qubits. If it changes in times, you know there is an error. And then, for example, you could apply a bit or phase, you can do a pi pulse to correct it back, although you can, in fact, you can keep track of it in software, but you know what's happened to the system. Okay, so so then again, you connect those two and you say there is an error in the phase. And the same thing here, as I said, you have an error here in your Z measurements. That means with a 0 went to 1 on the 4 neighboring qubits, and you know, it's clear that the correction is you have an error there. Okay, so you just keep track of that. And let's say, for example, you had a measurement, it was 0, 0, 0, 0, and then it went to the 1 state, okay? But it was only there by itself. And then the next cycle, it went back to the 0 state. So there was a change in parity in 2 cycles, 0 to 1 and 1 to 0. So it was a pair in time. Then you know that there was a measurement in the measure qubit. So you can figure it out from the pairs in errors and pairs in time. And that's the simple way. It's a little bit more complicated than this. And I'll talk about that in the experiment, but that's basically how you think about it. We okay with that?
Questions? One question about the maybe the previous slide shows it, the question better. So this phase diagram that you had for with about a bunch of CNOTs and stuff on it. So I think there's some confusion about this Hadamard. So it's the Hadamard is working on the data qubit down there. How is the measurement going to get it right when there's a Hadamard in front of it?
All I can say is, you know, I think you can understand why here there's no Hadamard. And all I can say is you have to go through it and see what the Hadamard does. And you know, you just have to work through that. This is called, what is it? This phase, there's some word for this, phase reflection or something and I think if you look in Nielsen and Swang, they'll talk about that. And, you know, you just have to go through the math. There's no intuitive way for me to see it. Again, if you go into the control Z basis, you see the symmetry, and it's obvious that you're doing a phase instead of that. Okay, again, that's a homework problem that you have to work through. Sorry.
Is that what people call phase kickback? Is that what it is?
Yes, that's the phase kickback. It's the phase kickback. And since it kickbacks a phase, then you need the Hadamars to turn the phase into a bit.
Very good. And also,
I find the phase kickback. I understand the concept, but I find that intuitively hard to understand. And I think by going into the control Z operations, for me, you can then see the symmetry. But phase, if you understand phase kickback, that's a great way to think about it.
So it's a question about this Hadamard and maybe all the other gates. The success of all this depends on the fidelity of the Hadamard gate.
Oh, absolutely. So the talking about the fidelity and the like is 2 slides from now. So good question. Right. We have to talk about that. Okay, so great. It makes me think people are understanding what's going on because you have the right questions, right? And you know, the whole problem here is that you have to kind of go through the whole explanation and then return to it to understand what's going on. So it's good this is getting recorded, okay? Anyway, so I've explained that you see errors in pairs in space or time, and then you decode, okay? Now, what happens is, in reality, every once in a while, you'll get a lot of errors. And for example, you take a look at this particular error thing, and it's not so clear how to decode this because, you know, they're kind of, you know, interacting with each other. And it's because there might be not a unique way to decode this, is how you get errors in error correction. And it's just like what I was talking about previously 2 slides ago. If you have too many errors, then you might correct it in the wrong way. And I'll explain that, okay? And in order to get not too many errors, you have to have not too many physical errors in the device, okay? And that means the device has to work pretty well, okay? And the basic idea here is that if you do a simple model of what you have to do, is you have to have the fidelity of each of the individual gates that's going on here to be greater than 99%. So you have to have an error of about 1% in order for you not to get confused. And then when you do that, the logical error rate will then go down as you make it bigger and bigger according to this exponential factor, and then you can make it small enough. Again, I'll talk about that next slide. Okay, how that works.
What if the error is during initialization of the data qubit? Can this system here detect that as well?
Yes, you do it in the same way as this, and I'll talk about logical qubits in a few slides, right?
One more question. In practice, how do you measure qubits of a surface code in a cycle? I think you had this. We measure qubits column by column, row by row, or what is going on with this cycle?
Oh, yes, good question. I didn't say that. All of these parity measurements are going on simultaneously. Okay, and there's a sequence to do this, so it's all simultaneous. It turns out, so you're doing this parity measurement and this parity measurement and this, and there's an interleaving between the C naughts or control Z according to a very specific sequence. If you get the sequence wrong, it won't work. So you have to do that properly. That's too complicated for this thing. If you go into our surface code paper, it'll describe the interleaving that's going on. But the important thing, you want to do this fast. You want to be measuring errors all the time, and it's important to do it in parallel. And this is how a regular computer works, and this is what you want to do here. And please note that some qubits and some architectures, you can't do things in parallel. You have to do it sequentially, which will slow down this, introduce errors, make it harder. And whether you're doing it serially or in parallel is a really big architecture statement. Okay. And not all the people, not all the qubits can do that. And that's really important to understand. But, demonstrating that you can do it, everything in parallel, simultaneously, is a big thing in terms of getting this to work. And in fact, when we get to the quantum supremacy experiment, I'll talk about that, because it's not obvious that you can do this. I mean, you can do it in principle, but to do it in practice is hard. Okay, were we good?
That's great.
Okay, now, okay. So now we're going to talk about the logical qubits. Okay, so if you can, here's a square array which kind of optimizes things. Okay, now in here you have 41 data qubits and 40 measurement qubits. So there's an operator left over that describes what is the logical qubit. And of course, the state is distributed among all of the data qubits in order to get things to work properly. Okay. So what is the operator that's left over? Okay. And the operator, you can write it in different ways, but let's just take these, what you call logical operators, between these qubits here. We'll call it X1, X2, X3, X4, X5. And the logical operator is just you know, it's kind of like a parity operator we've been talking about, but it's now over 5. But if the disk is bigger surface code, it could be more. And the Z operators are going up and down here. Okay. Now, the first thing to note is that if you take XL and ZL and you reverse the order in the commutation relations, because only one of the qubits overlap, you get a minus sign from commuting X3 and Z3. You know, XVOR and Z10, they'll just commute, but X3, Z3 gives you a minus sign. So these logical operators anti-commute, so it's going to act like a qubit. I mean, that tells you kind of the structure of what's going on. So you've made a logical qubit from here, okay? The other important thing, of course, is do XL and ZL compute with all the measurements states, all those things here, and they do, okay? So it's then stabilized, okay? So it acts as an extra degree of freedom in which you're going to store your quantum state. And I'm looking at this now, and I forgot to practice this slide, and I can't give you a simple explanation why XL and all the 40 stabilizers commute. I mean, for example, this one here obviously commutes with this X2, and it obviously commutes with the Z3, okay? And then this Z right here, it commutes with X2 because there's two qubits. And when you have 2 qubits minus squared is 1. So it's stabilized. I think that's the basic idea here. Okay, so it's the extra degree of freedom. You're not measuring it. And that's your logical state. And it acts like a qubit. And of course, with these many qubits, it's hard to state what exactly the state is. And what it turns out is you don't actually even know that. In the Heisenberg picture, you just need to know what all the commutations do. And then, you know, you can figure out the logic and how to use it. Now, let's go on a little bit more, okay? Hopefully this is answering some questions. You say, well, why, you know, do I choose it here? Why can't I choose it here or here or here? There's other logical operators. So for example, for the X logical operator, I can say it's X1 and then X6, X7, X8, X3, X4, X5. For example, it goes from one side to the other. Now, this particular new logical operator is related to the old one by the operator X2, 6, 7, 8, right? You multiply X2, 6, 7, 8 by this, the two X's that you see here actually sigma X, sigma X is identity. So that will go away, and then you'll get this. And you note that X2, 6, 7, 8, we measure, right? So we know what that is. So if these two, you know, so in fact, writing the X logical going this way gives you the same value, okay? It's the same operator, just with, you know, you have to change it by whatever that is. And it turns out that going from the left-hand side to the right-hand side in any path, you add all of these things and you get this same logical operator. So we talk about it in the simplest way. That there's an X operator going from left to right and a Z operator going from top to bottom in whatever way you want to choose. And we can change basis basically by these the known measurement parities.
Okay, couple questions.
There's got to be lots of questions here. So,
yes.
Great.
So first of all, put people at ease. A few slides ago, there were 2 X's together. Now there are 5. What happened there?
2X. Oh, I just changed the dimension of the array. So now I made it a square array. Sorry if that's confusing. Okay. You can make it an array whatever you want. And you'll see that you want to make it a square array because that's kind of the most efficient way to minimize the number of qubits you have to build, which you can kind of intuitively maybe see already, but okay.
And then one more. So we talk about stabilizer. We talk about sort of stabilize in different ways. Sometimes stabilized is an adjective. What exactly does it mean that something has been stabilized?
Yes, sorry. I've tried to not use the words like ancilla qubits and stabilizers because I think this is what's in the literature, but I find it kind of confusing. What happens is you have measurements of these complex parities, which of course are the stabilizers. And when you do that, that's something that's known and should be unchanging. And that allows you to know what's going on, say, if you don't choose this as your logical qubits, okay? Because that's information of what's going on in an array. And every time you run a code, these stabilizers things will be different combinations of 0 and 1, and you just keep track of it, and you keep track of the changes to know where the errors are. I'm sorry if I'm not explaining this quite well, but keep asking questions.
Are you depending on that the lattice has an even number of data qubits? What if it's 6 by 6 instead of 5 by 5? Is that good or bad?
To answer that question, you have to think about what the error rates are. Okay, because remember, for a fixed error rate, the larger you make it, the error rate goes down, and it goes down as the number, kind of the number of qubits. So you have to go to a certain thing. So d = 5 gives you a certain error rate from having too many errors. If you make it bigger, the error rate will go down. And of course, you can kind of see that the errors here maybe is going to be similar to the errors here. So square array makes sense if that's what you're thinking about. So yeah, and we'll talk next. Again, we're leading into the next slide of how big does your array have to be? You can have D here, whatever number you want. And the bigger it is, the better it's going to be, as long as you're below threshold.
Before you get to the whole error correction sequence, how do you know that you have prepared the correct logical state that you want?
So I will explain that when I talk about post-module operations. And it turns out it's actually trivial when you do that, but I will get to that.
So you're not really getting symmetry out on the edges, right? And the stabilizers are still working fine out there, yes?
Yes. And again, I'll get to, there's the edges, that's when I get to the end for the experimental part. There's some things you have to do with edges, but they're okay. You can figure that out too. I'll give some examples of that later.
That's all good.
But yes, you're right. You have to worry about the edges, and the edges add some complication to it.
All right, good.
Okay. So here you see the logical state. And now the question is what's the error rate? Okay. Okay, that's what this slide is about. Okay. So what you can do is you can take this array and simulate an error into it. And the way we simulate it, this is for the bit flip, or this is actually for the phase flip, excuse me. You can say that for each operation here, there's a certain error probability. So a certain probability P that it was one state instead of the 0 state, a certain probability here that the Hadamard gave you an error in doing this, and the C naughts and whatever, and you build a model for that. Okay. Now, of course, in reality, these probabilities will be different. Okay, and you have to deal with that experimentally. But in terms of, at least for these calculations, you just do it this way. And people have done calculations when you have these of different probabilities, so we know what happens. But for simplicity, you do that. And then you take a surface code of various sizes. Last time we were talking about 5, d equal 5, and you can go up to very large things, because this is actually, given their Clifford gate, this is easy to simulate. And you can say, okay, I put in an error, I have a certain decoding of how do you take that error and figure out what went wrong. And then you can measure what percentage of the time it decodes it incorrectly. And this is the logical error rate, okay? Do it for different sizes, different error probabilities. Now, what you can see for small errors here, this red line, is that your error probability goes down. The logical error probability goes down as these individual errors go down. Okay, so, you know, okay, you have less errors in the system. They're always going to be there. And the logical error goes down, but it goes down pretty slowly. As you make the dimensions bigger and bigger array, more and more qubits. You don't want to do that, but okay. You then see, as long as you're below a certain threshold, the logical error probability goes down very much more quickly. Okay, so you're trading off the fact that you can't make perfect qubits by making a lot of them. And that's what you do in error correction. And what you find at this threshold at which things get better, in fact, if you're above the threshold, making it bigger and bigger makes it worse, right? Because you're just having a huge number of errors. But when you're below the threshold, then as you make the error probability lower and lower, the logical error goes down. Okay, and you can fit the data to some p over p threshold, which is about error probability about 1%, raised to some power of dE given here, and you can kind of fit this in a rough way. Okay. Now, this is the important thing, is you can make exponentially small errors with making it bigger. And I kind of explained that qualitatively before with the simple 2-qubit example, and you can run complex simulations for both bit and phase flip errors and do that. Okay? And in some sense,
physical qubits, right? D squared physical qubits to get one logical qubit.
That's right. Yes, I believe that's how D, yeah. D equals 5, so 1, 2, 3. Actually, it's more than says D is just the number of data qubits here in the way that I defined it. It's actually D times D minus 1, all that squared, or some number like that. And it can be a large number. And see, the problem is, if you're way low probability, D doesn't have to be that big to get a little logical rate. But if you're just barely struggling to get it before the threshold, then D has to be very large. And, you know, I would say, don't think of this negatively. It says, even though it's hard to get large probability, if it's low enough, then you just make up for it by making lots of qubits. Mm-hmm. And, you know, if you look at your classical computer where you can have billions of bits, okay, well, maybe making thousands or millions of qubits in 10 years or 20 years or some number of years, we'll know how to do that. And we don't have to make perfect qubits. That's great. And in fact, that's the magic of error correction. Mm-hmm. Mm-hmm. Okay, so that's wonderful. But okay, it does mean you have to do it, and it's you know, it's maybe quite a few, but okay, you can do it.
You can do it. Top right corner, you have DE. What is DE again?
Where P?
All the top right corner of your slide here.
Oh, I think that's hidden. Yeah, that's the this DE is the power law that you see here. Okay. So you can fit this data to 0.05 times P divided P over P threshold, which is 1% to the DE power. So from this is the this is the error kind of dimension.
Mm-hmm.
Okay, so as you go to larger distances, this gets bigger, and then this gets suppressed in this with this polynomial way.
Mm-hmm.
And it's actually exponential. Okay. Okay.
John, can I ask you if you have any plans for a 5-minute tea break?
Whenever you want.
It's whenever you want. I think that some people would like to get.
I'll keep talking until you want to give a break. My goodness, I've gone through a small number of slides and it's been an hour and a half. That's great.
So John, let me suggest that a 5-minute break just to go get a cup of tea, and then we pick it up then. How about that?
So let me do this. The next slide breaks into, let's do it after 2 slides.
Yeah.
Okay.
Good.
But
then the problem is, then I want to ask you a few questions also to pick up some things. But then, good plan. So let me just ask. So early on, you talked about errors that are seen in pairs. But now, a very short time ago, you start to talk about 5 X's in a row. So how do errors that come in pairs match up with 5 X's?
That's in the bottom left.
Ah.
Okay. So what I'm going to do now is explain this formula here and why it works this way.
Mm-hmm.
Okay. So you take, for example, your logical operator going from left to right. It's a square array, but let's just take this d equal 5 and think about this logical operator that goes from here to here. Okay. And let's say you had an error measured in this qubit and this qubit and this qubit. So it's an example, but you'll get to see how this thing works from this simple example. Now you need to decode that, and it happens in pairs. Okay, so the obvious way to encode that is these two had here, it was an error, and you decode it as an error here. This one here had an error. It can be equal this qubit or this qubit, but because there's no change here, you're going to decode it and say an edge one. So the edge ones don't come in pairs, but you can still decode it, right? You still have the information. So you decode it as an error here and an error here. Okay? That's the simple way to decode it. Now, you can also decode it as the complement here, where you have an error here and an error here and an error here. That also solves for the decoding of what happened. And if you notice that this down here is the complement of this here. So as I talked about before, there's always a complement. Now, the thing is that this has 3 errors, and the probability of doing this is going to go as this error probability and the individual qubits cubed, because there's 3 errors. Whereas this one here only has 2 errors, and that's going to go as p squared. So if you have to choose between which one it is, you're going to choose this one because it's more likely. And if this is what happened, then you'll correct, and it'll be possible. The problem is there's a chance, it's a small chance, but a chance that it's going to be in the bottom p cubed. It's going to be p cubed. It's less likely, but there's a chance. You're going to decode it this way, and then you're going to get a logical error. Okay, so that's the basic physics. Now what you do is to say, hey, let's be a little bit more quantitative. And you say this logical error, there's actually 8 ways that you could have there's 8 steps here. So it's 8p cubed, okay? And then you can say, look, there's a whole combination of ways in which you can get a p cubed error, where, very different, lots of combinations of getting the red dots, right? So it can be a red dot, here and here and here and, et cetera. So there's this combinatorial thing. Again, this is high school statistics. You have a different combinations. There's multiple ways you can have a probability. So you're writing some very simple combinatorial thing. And in general, for a dimensions D, and this error dimension DE, which you can compute from here, here's the general formula. Okay, go through the statistics.
Mm-hmm.
And then what you do is given that formula for the logical qubit, here's your thing, your prediction. And you see, okay, the crossover part's a little bit different, and that's because this is simplistic, but you see the slopes here are all correct. Okay? From all the way up to 55. Slopes are correct. Okay, and it basically describes what's going on. So it just says that what happens is you get a lot of errors. There's lots of combinations. Some fraction of the time, there's so many errors that you decode it wrong. And there's this simple, it's a combination and it's a total error rate to some error dimension that gives you that physics. So that's close enough. At least you understand what's going on. Okay, you use this formula, from the simulations, but conceptually, what's going on. And again, this is a very simple calculation of one thing. You have to include the whole array. There's more errors. There's more combinations than this that pushes it out. Okay.
In the formula up there, you have PTH. Is that a function of just the hardware, or is there more to it than that?
No, that's a function of the just the architecture. So for the surface code, this threshold is 0.01. It has to do with a given error model here. Okay, different error models. You put different P's here. It'll be more complicated formula. But you can write approximation formulas, but it generally goes like this. Okay, but the important thing here is it tells you what you have to do. You have to get below a certain threshold, and then you have to make it big. Okay, that's what these curves tell you. Now, it's interesting to think about this threshold. If you just had this term here, P, in order for this to get to exponential suppression, P would have to be 1/8, which is 0.125. What gives you the 1% is the fact that you have all these different places where the errors can be. Okay, it's a combinatorial thing. So you have to do more qubits to get this small, but then this hurts you, and that's what gives you in the end why the threshold is per operation is less than what you would naively guess.
So for the simulation thing that you have at the bottom there, what error model do you use? Is that a depolarizing error model, or what do you use?
Yes, this is a depolarizing error model, which is a certain rate for you to go to any of the other states.
Very good. Would you take a couple of questions on the previous page?
Yes.
So are you saying that on the okay? So we have a purple. Where was there was a purple one that somewhere, a purple square somewhere that showed up. Is that the logical X operator that we are looking at there in the purple square?
What I'm saying is the purple square is one of your measurement, stabilizers. Okay, it's that what that operator is. It's equal to +1 or -1. You know what it is. Okay. Mm-hmm. And then what I'm saying, so since you know what it is, if you decide to make your X logical go up and down here, still goes left to right, you know what that operator is because it's just related by whatever X logical was here with a factor that you know. You just multiply it by this. So it's a way to say that this logical operator just takes qubits from wherever you go on the left side to wherever you go on the right side. Mm-hmm. That's what it's saying there. Mm-hmm. Because however you want to wander through that, you wander by applying a known measurement value to it.
Mm-hmm. Mm-hmm. So we're looking at this blue across and red up and down, and they intersect in the middle at a white qubit. is that picture repeated at every white qubit, or is it just that thing in the middle and only
Yeah,
that?
in some sense, you could say you can move your red to the left or right and the blue up and down. It always intersects once, okay? And it's a logical operator, however you choose it.
Mm-hmm.
And you see the fact that you can move these blue and red operator lines kind of makes sense because you're distributing the logical states among all the data qubits. So, the fact that you can move it, whatever kind of makes sense. And like I say, as you move it, you can calculate what the new value is going to be.
Mm-hmm.
You know, because you know what all the measurement, stabilizers are.
Why does this XL, why does it reach all the way out to the edge of the picture? Why not stop earlier?
That's when you talk about what this extra state is, that is the natural way, that's just what it is. Okay, that's what gives you the acting like a qubit, and that gives you that it commutes. Now, the story is a little bit more complicated than this when you want to have multiple qubits. And I'll talk about that in a few slides when I talk about logical operations. Again, good question.
Another question about the simulation from on the next page. Are you simulating just error correction here, or is there an underlying algorithm that's getting error corrected as you're simulating?
No, this is just simulating error correction, and how often you get an error in your logical state. Only that. And doing logical gates, again, I'll talk about after the tea break.
Okay. And one last question that that sounds like this: is surface code topologically safe from errors?
I don't know what topologically safe means, but there is a topological operation we'll talk about later. So I'm going to guess that it's correct, but I need to know what that means.
We'll ask for clarification. Thanks. Very good.
Thank you. Okay. So this is great. You can predict the error rates, and from simulations you can put in different probabilities. This is not too hard of a simulation. You can understand how it scales, conceptually, approximate it. So this is all very good. And basically, what you can do is take this formula, which is we define this term lambda, which is how far better than you are the threshold. So if your error probability is 1%, lambda is 1. If it's 0.1%, one error in 1,000, it's lambda is 10. And basically your logical error rate goes down as this formula. And what you can do is you can just plot this versus the things you have to control with an experiment. The physical error rate, how far below you are from the threshold, and the number of qubits you need. And again, if you aren't far below the threshold, you need lots of qubits, exploding number of qubits to get a low error. So you want to be significantly below the threshold. And for example, if you want logical error rates of 10 to the minus 5, which is about, let's say 10 to the 5 logical operations, that'll run your quantum computer for about a second or so. It's this blue line. If you want to run it for a day, that's red line. If you want to run it really long, 10 to the minus 20 errors, which are kind of the errors of classical rates, well, you would need more qubits. But you see that it's kind of, it's a log scale, but okay, if you make enough, it's only, it's just a log scale here. Okay, so what I would say is when you look at this curve, you don't want to be here where it's blowing up quickly. So you want to target a physical error rate of about 0.1%. So 10 times below the threshold. And then you'd say you want to run it for a day, which is typical of some algorithms. Then you want about 1,000 qubits. And other maybe bigger algorithms, you may need a few thousand, but you can also work on making the error rate lower, right? And then you have fewer qubits. So you can calculate what you have to build. And the basic idea here is you need about 1,000 physical qubits per logical qubit. And you basically need about a 30 by 30 array so that this exponential factor is big enough. Or say 30 by 30 array, something like that. So you know what to build.
Could you repeat the what lambda is in this formula?
Lambda, it's right here, lambda is how much better you are than the threshold. So if your P is equal to B threshold, you're at 1% error, lambda is 1. If P is 0.1, so you're better than the threshold, then lambda is 10. And then PL, because there's a minus sign, it gets better and better, as you make it bigger. So for us, measuring lambda, how good are you compared to the threshold is key. And of course, different architectures have different thresholds. And the whole thing is, can you build a system where you lambda? And when we build a system, we want to measure lambda, because that will tell us how many more qubits we need to build to get it to work. And if lambda is less than 1, then an infinite number of qubits will not work. If lambda is 0.8, we're going to have to make a huge number of qubits and it won't work. So, we want to get, lambda, we want to make lambda big.
Maybe even a bit more. That one, let's look at that one. So it says here that if we look at diagonal from top left to lower right, then can a diagonal, it says here, can a diagonal be both XL and ZL, so logical X and logical Z that have 5 overlaps?
I've never thought of that. I mean, I think you would have to go and, you should be able to compute whether that's possible based on this. In terms of this, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9. Since it's an odd number of qubits, X and Z would anti-commute. So maybe it's possible. Again, you would have to sit down, and I'm telling you what's important here. The fact that however you define this, it acts like a qubit, and then it would commute with all your measurements, all your stabilizers. As long as that's the case, it would be the thing. The one thing I would say is, although this kind of explains how it works, the way that you build multiple logical qubits is a little bit different than this, and this is a little bit of a simplistic picture. Okay, I mean, you can see that this could work, and this is how you're going to do the first surface code experiments. Is you're going to do this, but a full quantum computer will be a little bit different, and we have to get to that step. So these are good questions. Okay.
There's a question that comes up in different ways multiple times. How is the logical qubit state actually preserved with all these physical qubits doing all this kind of stuff? How is there a sense of that the logical qubit actually is working correctly?
So the logical qubit is preserved as long as there's a small logical error rate. Okay, and that's determined by this plot right here. So it's preserved as long as the errors are low enough, and it's big enough, and then you preserve that one logical state.
Very good. I think we're good.
Okay, good. It's kind of hard because you have this bias towards thinking about what the state is, whereas what's really important is, how can the state change? How can you get bit flips or phase flips? And can the logical state change in some unpredicted way? And then it's only when I get to the next slide, when I talk about real logical qubits, that I'll talk about how to like initialize the logical state. It's not obvious how to do that. So in fact, you do that with measurement, okay? And again, going to this, I'm going to just fly over this, just give you a general view of what's going on. This gets enough complicated that if you want to understand the details, you really have to go into the physical review A surface code. But I'll give you the basic essence of how the logical states get made. That's what I'm going to do next. And I think at that point, okay, let's see. That's the end of this section. But okay. So, you know, again, it's very important to know how the logical qubits work.
So while you're still here, in the picture with the computed error on the data qubits, why did you black out 2 qubits? So let's see. Is that the one down in the bottom left corner? Why are 2 of them blacked out there?
Yes, so what happens is the black qubits, okay, oh my God, that's a mistake, I'm sorry. There was an error converting this from PowerPoint and various things, and that's just a mistake. Yeah, that's just a mistake.
Okay, all right.
That should be an open circle.
Got it. I think we are done with the questions for this set of slides here.
Great. Jane, I think we're going to get started soon. Okay, shall we get started again or a few more minutes?
I think we're good.
Okay. So now what we're going to do is talking about logical qubits. And we've talked about the square wave before. That was one logical qubit. And okay, that's the first thing we're going to do to check it. But of course, you want to have multiple logical qubits and you know, multiple measurements, okay? So multiple logical qubits, and you want to have to interact them. So it turns out that the way you're going to make more practical logical qubits is to make a big square array, but to produce holes in them to store the qubit states, where we stop doing the measurements. And I'm going to give a simple low dimensional example here, but if you want to have high dimension, low error rates, this hole is going to get really big, and this length here is going to get really big. Okay, but we'll just give a simple example here. So what we're going to do is, it's an interior surface qubit, and our X, we're going to have 2 holes, and then our Z operators on this hole is going to be, well, there's going to be 1 hole here, and then this will be the logical Z's, and this will be the logical X's. Okay? And just like the other thing, you can move around these Z's and X's to have other things, but this is kind of the simplest, more straightforward way to think about that. Now, the question is, how do you initialize, let's say, this qubit to a Z logical, right? You can't initialize both Z and X logical because they don't commute. So let's initialize Z logical, which is either going to be a 0 logical or a 1 logical. Okay, so how do you do that? Well, what you do is you run the surface code so that you're measuring this Z logical, and it's either 0 or 1. Okay, you just measure that. And at some point, you just turn it off. And then you have to go through it carefully, but it turns out that you can error correct in the step where you turn it off. And you know that as long as the errors are low enough that you're now encoded your qubit state into a Z logical equal to whatever you measured it before. And it's not like you have to know that it's a 0 or 1. It could be either 0 or 1, and then you can modify what happens with your algorithm past that so that you're doing the right algorithm. And again, you have to go into the theory algorithms to know that you can do that efficiently. Okay? And then at the end of your calculation, you want to measure ZL. And then what you do is you just turn it on again. And then you measure what ZL is. So by turning on and off the Z measurements, you can do an initialization and doing measurement. Okay? Now, what I want to talk about next is how do you do a logical C0? And what you do is you have a pair of these holes, as I've given here, and then that forms some X logical gate. And you have another pair down here in the same way. And then you move this hole here around. And what you can see is you can move the hole by, again, just like initializing this, you can, for example, turn this off, and you know that the X logical is whatever it was before times the measurement. And then in the next step, you can leave this hole and then turn this measurement on. And just because you can do a measurement, you then know the logical state of the new thing. In fact, you can turn on and off a bunch of these things in a row so that you move in one step all the way out to here, and then the second state, you move it back to here. And it turns out when you look at what happens to this, this is equivalent to a C0 operation by braiding. And there's a topological nature of this device through this particular thing that's very beautiful. You can compute why it does that in the paper, and it allows you to do the C0 very easily. Okay?
You talk about turning on and off here. Is that by changing the coupling between the qubits?
You just, you just turn on and off the surface code sequence, right? So there's a sequence I showed before, and you just don't do it. You just turn it off. Mm-hmm. Okay? You don't do it. You don't get information. You don't project the state, right? So, you know, and then you do that, and that state doesn't change because you're still looking for errors in the fabric around that.
Good.
Now, it turns out that the C0 is relatively straightforward via this braiding operation where you turn things on and off, which is what you're doing with measurement. It turns out you have to have single gates such as bit flips and phase flips. Those that can actually be done in software. It's efficient to do that in software. The Hadamard is more complicated. Again, it's in the state, and you also have to do a non-Clifford operation where you do a Z rotation, but you do it half as far. So I think it's a 45-degree rotation. And this is square root of Z. This can be done efficiently, but you have to do this is 90-degree rotation. A 45-degree rotation is hard. It's non-Clifford, and you have to build that. And this requires a lot of work to build. And again, I'm not going to give it here. It's based on building up all these kind of things. I would say 90% of your quantum computer is making that gate. So it's very important to do it efficiently, but it's beyond the scope of what I want to talk about here.
In this C0, which one is the control and which one is the target?
I have forgotten.
Okay.
I'm guessing that the one you're moving is the target, I think. But again, I go back the paper, it'll be all in there. I've forgotten.
So Austin Fowler yesterday talked about lattice surgery. Is that related to all the C0 stuff here?
I believe that's the technical name for it.
Okay.
But I would have to check. I would check to make sure if there wasn't any further comments there. But that's the basic idea.
Mm-hmm. Mm-hmm.
It's some jargon, and I'm more trying to emphasize here, what's going on with simple vocabulary.
Just a bit more about the picture here. The two logical qubits. What are they, and what are the exact set of physical qubits that construct those logical qubits?
So what happens is you make a huge array, much bigger than I was talking about before, and then by stopping the measurements, you create this pair of holes, which gives you the logical operators, kind of like what I talked here. Note that this logical operator here, that kind of goes around here, commutes with this because it shares one qubit. And you can show that these logical operators compute with all the measurement stabilizers that's all around it. It's the same thing that I described earlier for that. So now let me make one statement here that's very important. What's really nice, when you look at various coding schemes, you have a certain coding for for getting low error rates. And then you do something pretty different to make the logical gates. Okay, and it's a very different thing. The beautiful thing about the surface code is all you have to do is build a big array, and it's a big array. And then all you have to do is turn off measurements and do some other things that are within the capabilities of that to scale up and do multiple logical operations. So you're not building anything new. You're still just building it bigger, okay? And that's the whole point of scaling a computer is, hopefully if you know how to make a small one, you just have to learn how to make it bigger and bigger. And in this case, you turn on and off Z measurements, which we know how to do. And then you can do the logical operations. So there is more overhead and whatever to do, but it's conceptually you're doing the same thing. So there's a nice roadmap that you have to make to go from error correction to then logical gates. And the physics is more or less stays the same. It's just having this more complexity to it.
Is the logical X the same for all the qubits when you use this code?
The logical X you can do in software. So you can say, okay, I want a bit flip, and then you can just keep track of that in software in order to do that. However, for the Hadamard and let's say a square root of X, which is a NOT gate, then you have to do some hardware operations. And again, I just refer you to, as kind of complicated this is, this gets so much more complicated that you're just going to have to read the paper, okay? People know how to do it. But what I would say is, once you understand how to build what I've talked about so far, you know what to build, you know what to test, and then hopefully all of these other operations are just the control software stack onto what you already know how to do with I told you so far.
Okay.
More or less.
Let me just say to the people who have asked questions, I think we should move on so John can get to talk about the rest of his stuff. So I believe you are at the end of one set of slides here very soon.
Yes, that's right.
I think
so I'm at the end. I'm at the end here, and now I'm going to go and talk through the rest of the talk. Okay. Very good. I've given a pretty detailed description of what's going on with this, and I just want to try out another high level. It's a one slide description of what's going on here. okay? And this is more for people who know something about electrical engineering and how computers work. So if you know how the computer work, I want to say what's going on with the quantum system, because things are different, but there are some similarities. So I'm not sure for the physics crowd, this will teach you how classical systems work, but I think it's kind of interesting to think about error correction in this way. So let's talk about how computers work, okay? Computers work with a memory element you call a D flip-flop, so that every time you have your clock go from low to high, 0 volts to 1 volt or something, then whatever is on the data line, that gets stored in memory and puts to the output of the Q line some fraction of a nanosecond later, okay? And then you run a clock at every nanosecond or so for a gigahertz processor, and then you do processing. And what happens is you have whatever data is coming out of here, it goes into a bunch of logic gates, which in the end are and OR gates and NAND gates and whatever, more complicated gates. And it does a bunch of that logic, and it computes from one period of time, what's the state of the computer at the next clock edge. So it's one state to the other. And in fact, this kind of logic, thinking about one state transferring to another state via these clocks, is really what's going on in the circuit model of how you build a quantum computer, okay? It's just a little bit more complicated. So what goes on in a quantum computer is that you have your quantum states, and then you go into the next quantum states. And one of the things you have to do is do classical error correction and decoding and logic on these quantum states to correct it in some way. And one of the things you have to do is turn on and off the measurements and braid and do other things to do the logic. Okay, so this is kind of combined here, but it's the same. Now you have to change, you can get bit flip errors, as we've talked about, and the classical error decoding logic will do that. It'll more or less keep track of it in classically, those bit flips, and then when you want to do a more complicated logic operation, it will change that logic operation in some way to do that properly. Okay, so that's the thing. But what's more complicated in the quantum computer is that you still have a clock, and the clock has to do with the phase of the qubits. And instead of the clock being synchronized externally by external signal, the clock, in the sense, is what's going on in the qubits, okay? And they are either the phase isn't changing, in which case it's an easy clock, but in any practical qubits, these qubits are, say, oscillating at a few gigahertz. And what you need to know is, since this clock is something going internally, you need to know if the clock is drifting or doing something wrong. And in some sense, the phase correction of the quantum computer is to check whether the clock is working properly and put in some phase corrections because of the small errors that you're getting from the clock drifting. So that's why qubits have to be made as very stable oscillators, and why, for example, in ion traps, it's very natural to think about an ion trap as a quantum computer because they're good clocks. Now, it turns out that in superconducting qubits, there's nowhere near as good of a clock as a ion trap, but it's good enough so that you can do the error correction and stabilize this. Error correction corrects the amplitude bits and aligns the phase in the clock every round, okay? And you're kind of making a quantum flip-flop through the error correction as we hear, and then you do the logic and do your correction. So this is, I think, very important because from an electrical engineering point of view, this kind of tells you the complexities of this and how one of the things you have to do to make good qubits. Any questions here?
So you touched on this thing with different quantum computers. Are there different techniques to physically make X gates and Z gates, even on the same kind of technology as superconducting, or do all the companies, for example, for superconducting qubits, make X gates and Z gates in the same way?
So, for example, the X gate is typically driven by a microwave signal that's resonant with the qubit transition. And then you just, flip, it makes a transition through an oscillating signal. And this has been studied in quantum mechanics on various signals, and different qubits have different frequencies. Now, the Z gate can be made with a combination of microwave signals at different phases, which those different phases encode themselves into the qubits. In our particular qubits, we can adjust the qubit frequency with essentially a DC line, and then we can adjust the phase that way. So there's a variety. The phase is a little bit harder, but that can be done. And unfortunately, I haven't gone into that into my talk, but these are quite well known. And people, you look at each qubit technology, people have worked hard to make good things. Now, what's more complicated is making a 2-qubit interaction and doing that well. That's much harder. And there's a variety of ways to do that. And even in superconducting qubits, there's maybe 5 or more ways to do it now. And people are exploring how to do that. And that's a big research and kind of beyond the scope of my talk here. I'm really focusing more on the theory and practice of error correction at a higher level.
Very good.
Okay, let's go on to the next slide. Now, although I've told how the surface code works, hopefully in enough detail that you kind of understand a little bit of the complexity, what I next want to do is do a high-level description of the system requirements to make error correction in both a general kind of statements here and in terms of the surface code. And the reason I say that is that it's very important now that people are looking at all the different codes that you can do. This is really good. We want to try to make things better. But I want to inject a dose of experimental reality into this, in that, for example, the surface code uses a lot of qubits. Let's try to reduce the qubits. But there's a lot of things going on here. And the reduction of the qubits is not the only game in town in terms of getting this to work. Okay, so I want to go over, I think these are 10 or 11 problems that you have to think about. And that it's good to explore all the different kinds of coding, but in the end, you have to go into these kind of questions and more to know whether this is actually can be realizable in an experiment. So, and then, yeah, so let's go through the high level things, the milestones you have to get. And of course, the hard part is you have to get every one of these and more to work well at the same time. And not all codes do that. Okay, so I would say the most important one is the threshold. We need to have the error per gate of the physical operations to be, let's say, 10 times below a certain threshold or so, has to be below it. And or else you can't build the quantum computer. And I'm going to say what's great about the surface code is it's 1%. And I believe that is basically the highest threshold that people know about right now. And one of the reasons that threshold is so high is it's a very simple, architecture. You're only connecting to the 4 nearest neighbors, and that makes it less complicated and better. Okay, so the threshold is good. If your threshold is 10 to the minus 4 and you have to make 10 to the minus 5 qubits, then that's, you need to know that. Okay, the next thing to do is as we talked about, is you need to know qubit number, and let's just say the 10 to minus 10 error. Okay, it's an exponentially small error, because when you run these complex algorithms, you're going to do a lot of gates. And for the surface code, it's about 1,000. Okay, now, of course, this number is depending on how far below threshold you are. If you have a threshold of 10 to minus 4, 10 to minus 5, and you can't make a qubit that well, then this number is infinite. Okay, so you have to think about the absolute number. Next thing you have to do is talk about architecture. In the surface code, it's 2D array, 4 nearest neighbors. Other architectures is more complex. And what happened, this is basically very much coupled to the connectivity of the qubits. And the problem is when you build qubits, the quantum nature of this means that there's lots of ways to have errors if they're connected together, or even if they're not connected logically. It makes things way more complicated. It's way harder to build a complex connected architecture. And that will throw itself into the threshold and qubit numbers and other things. So you have to think about that. The other thing that I haven't talked about much, but when you get these error pairs in the case of the surface code, but there'll be similar things in other codes, you have to decode that into what actually happened. And even with the surface code, which is a very well-known minimum weight matching algorithm kind of classically known, there's a lot of work on that. That requires a supercomputer, more or less, to do that decoding real time. There are some codes that are known to be NP hard to decode. So maybe there's approximations and the like. But if you take something as simple as the surface code, and to decode it, you have to use a supercomputer. It means that the decoding complexity is very important when you decide a new code. And you just have to say what it is. And maybe you don't know now, it's something that people have to work on. But if it's really complex, it won't work. Okay? Now, these 4 are kind of the main things for the physical gates. You then have to think about logical gates. So, can you build a single qubit logical gates? You have to show how. Can you have a CNOT gate? How do you do that? The braiding that I talked about is really elegant and simple. And in fact, you can do multiple CNOT gates on one move, and so there's some efficiencies there. The measurement, you have to be able to do measurement. In this case, logically, we turn on and off the error correction. And so it's physical, and okay, that's easy. Can you do parallel logical gates? Can you do long distance logical gates? And then 90% or more of your quantum computer is your T-state distillation, this non-Clifford gate. And can that then be done efficiently? So you need to know all these things. So, you start with this and you work through that, and that's really good. The one last thing I'd like to talk about is your sensitivity to correlated errors. When we talk about the surface code or any error correction working, you're talking about having errors that are uncorrelated from each other, independent. That's why the statistics works. If you have some event that causes many qubits to flip, bit flip or phase flip at the same time, that correlation will mean that your error probability is going to be high. Okay? And we're at the beginning of this field, but there can be a variety of things that can give you errors. And for example, very recently, I've written a paper on it. The Google group has done a nice experiment. Other people have talked about it. And although the average effect of cosmic rays are very small in a qubit array, when you do get an event, it affects neighboring qubits. And, you know, we have to measure how big the patch is and whatever, and how important it's going to be. But there are error mechanisms that we're going to give you correlated errors. Now, the nice thing about 1,000 qubits, I'm saying there's an advantage to a lot of qubits, is that if this affects 1 or 10 qubits, that's way smaller than 1,000, and you're going to be able to correct for that. But let's say you find a magic, qubit that only needs 1, let's say Majorana qubits, or 10 or 20 qubits to encode, which is great. It's a way number of less qubits. Everyone's trying to do this. But you see correlated errors, then you're in trouble. And you don't know what the trouble is until you start understanding about correlated errors. And very few experiments are out there to understand that. And the cosmic rays is an example of one where people are beginning to understand. So this is a statement, again, as when you think about system requirements, there are competing system requirements, and this one here and this one here kind of talk to each other in the design. Now, for example, for the surface code, I think bringing the number from 1,000 down to 100 will be great, okay? And definitely, I think you can fix it so at 100, you're not going to see that. So bringing it down is important. But I'm not quite sure you should bring it down to 1, okay? Unless you really work out all the physics, which has a lot of unknown right now. So be aware of that when you're thinking about error correction, that there's a lot of things that has to go right in this. Is there any questions on this? Because I'm now going to go to the kind of the more experimental part of my talk.
Let me just bring up 2 questions. The first is the analogy between flip-flops and error correction codes. How deep does this go? And in particular, would quantum error correction, in a sense, be a quantum flip-flop?
Yeah, I think various people would argue how close of an analogy that is. All I can say is when I was forced to explain this to talks to electrical engineers to kind of give an analogy, which came from a talk, this particular thing really helped me understand how to build the full quantum system. So I find it useful. I'm not sure everyone will find it useful, but if you want to explain to electrical engineers, computer engineers how it works, I think it's quite useful. And I actually find it quite useful because it helps me understand the similarities and extensions you have to do. Mm-hmm. But again, I think that'll depend on the person, whether, and what you're thinking about. There's a huge stack in building a quantum computer, and you have to understand that stack.
You said that we need 4 nearest neighbors at least to make all this work. Would it be good to have more than 4?
So you can do that, and there are surface codes that can do that, and it'll probably lower the number of qubits you need, or maybe simplify some of the logical, say the T-state distillation, but it probably will increase the threshold. And see, so what you have to do is when you do that, you have to say, okay, you have a new architecture. What are all the system requirements here? And you have to go through and say, compare it with the surface code, these and other things, and then see if it's practical. And you just have to check it. The thing about system requirements is you can have 9 good things and 1 bad thing, and that'll make your architecture unworkable, right? Now, what happens in physics papers is you tend to emphasize the good things, which is nice. That's good research. But if you actually want to build things, you have to emphasize all the, what could be the bad things. So although it's great to be an optimist to generate these new ideas, you need a dose of maybe pessimism, maybe it's a dose of realism to know what you have to do to get it to work. And that's hard. And I'd say that's the forefront of research right now. And that's the reason I bring it up, as if young, people are thinking about doing this and whatever. It's great to work this out, but you guys should be thinking about your system requirements. And here's a small list.
Very good. So now I'm anxious that you get to cover your whole plan before the hour is up. So I think you should move on to your next point.
Okay. We'll get as far as we can. And I think I might skip a section, but we'll see how quickly this goes. Now, we talked previously about error digitization. We say there's a probability of nothing happening and doing that. And then the obvious question is, when you think about what's going on with the state, you can be, say, starting in the 0 state and in the block sphere, making a small small rotation, so it's a small amplitude of being in the 1 state. Okay, so what happens in terms of error digitization? You can think about this in terms of what happens when you measure the qubit. And when you measure the qubit, what measurement does, with probability of 1 minus epsilon squared, which is the rotation here, this state goes into the original 0 state if you measure along the 0-1 basis, and it goes into the 0 state, the perfect state, but with a probability. As a probability epsilon squared, where this state goes into the bit flip state 1. So you see when you do a measurement, you take a small error and you quantize it, you digitize it. And this is why it's okay to talk about probabilities of perfect thing and having an error. Okay, this is the motivation. Now, although this is a simple example of a 1 qubit, you actually can see error digitization if you look at the time evolution of a density matrix. That's assuming you have constant error rate, and there are ways to get around that, that's where the error is proportional to time. So although I'm motivating this in terms of a measurement, and of course that's happening in the measure qubits and the stabilizers, it's happening there, it's kind of a more of a general process of quantum mechanics. And it turns out, looking this approach, you can talk about it in terms of small rotations, or equivalently, you can talk about it in terms of digitized errors. And either one is okay. It's kind of magic. Okay?
Mm-hmm.
Okay, so I want to talk again, I'm going into the experiments now. I want to talk about testing this assumption of digitized errors. Okay, and this is a question we had previously. I just talked about it here. It's a fundamental assumption of the error model. Is this really good? Okay, and the talk I'm going to give on this is actually the talk of the quantum supremacy experiment, which I assume people know a little bit about. So I'm going to go through it quickly, especially with only an hour left. But I want to emphasize the part of the experiment where we test for digitized errors. And in fact, of course, quantum supremacy is great for other reasons, but that was the real interest in my mind of testing quantum mechanics to see if this model really worked. Okay, so let's go into this. So we have a Josephson junction, which is a macroscopic device. The junction is about a micron in size. This is a fraction of a millimeter in size, and it's basically an electrical oscillator between the capacitance of this island to ground, where it's brown here is where the aluminum has been etched. And then we have crossing of 2 aluminum wires with an oxide layer that forms essentially a nonlinear inductor. And this inductor capacitor forms a resonator at about 5 gigahertz. And it turns out that this Josephson junction is nonlinear, so you can map this to a pendulum. And you know from classical physics that the pendulum lowers its frequency as the amplitude gets better. So the 0 to 1 frequency is 5 gigahertz, the 1 to 2 is about 4.8. so that you can, with a long enough pulse, just stay in the 0 and 1 state. So here's a classical analogy. 0 is in the ground state, 1 is the first excited state. You can draw wave functions of this in terms of the charge or voltage to understand what's going on. And then we bring control lines into here to make transitions between 0 and 1 by putting microwaves at their 5 gigahertz transition frequency. And this is a squid, and we can change the inductance and change the frequency too through a DC current into here. Okay, I'm going to go fast because we don't have as much time as we'd like. Now, what we did for the quantum supremacy and the Sycamore processor is we built a 2D array of qubits that is compatible with the surface code. And it turns out that for doing experiments, this diagonal kind of surface code is a little bit more compact in terms of seeing smaller logical errors. I think you could see that these X logical operators that go diagonally are a little bit longer that way. I think that's the idea. And again, these has 4 nearest neighbors, 4 compatible to surface error correction, and the like. And we've built a new device where we can do kind of standard control of single qubits, but we built basically an adjustable coupler or switch to turn on what would be the control Z interactions between neighboring qubits, or swap operations in that case. So we can turn that on and off with the classical signal. It's more control wires, but it allows you to build things better. So, you know, in the end, you want to get it to work. That's what we do. And we then put it in a package here with mu metal infrared shielding, microwave connectors. We then put it in a dilution refrigerator, and then have lots of wires going up to room temperature for the control, and some quantum limited microwave amplifiers to measure the qubit. And then that's in a dilution refrigerator, and a lot of wires go to room temperature, custom built control system, high speed, high precision, that can put on the microwave and DC pulses to control it. And then of course, there's a huge software stack to calibrate and control everything. And there's just a lot of physics and a lot of software engineering to get that to work right. Okay, I want to talk a little bit about error characterization. And you want to know the errors of your device. It's a critical thing. So what you do is at the base level is you do tomography, which is basically having, let's say, a 2-qubit gate that you want to calibrate, and you have a bunch of single qubit gates that are NOT gates or square root of NOT gates, Hadamards, whatever you want to do. And you start at the 0 state and you measure the output state, and you measure what the output state is for a bunch of different gates here. And then from that, you can use tomography techniques to back out what this gate did. And it works fine. It's most fundamental. You get a full quantum description. People have been doing this a long time. There's clever ways to do this. The problem is in the end, you want to make this with 3 nines fidelity or so. And your state preparation and measurement, these have errors in it. And it's hard to separate out where you're getting errors from all of these things versus error to this. And this is called spam errors, state preparation and measurement errors. And that's a big problem with this. It's obvious, it's not obvious how to improve the gates sometimes from this, although you can get information. And of course, this, with all these different combinations you have to do with tomography, it scales badly and it's hard to do beyond a handful of qubits. You can do it, but it's just really kind of impractical. And you know, and also this full description is not what you need for error correction. What you need to know is kind of the average error for doing that. So over the years, there's been something called randomized benchmarking. And what you do in randomized benchmarking, you take this and you just repeat it over many, many cycles. So now most of the error is happening in this repeated cycle. And a small contribution of relative error comes from your state preparation and measurement. So you kind of amplify the errors that's happening in all your gates. And you can now you can subtract away the state preparation and measurement by measuring this versus the number of cycles, and you can get the information. This is much more scalable, but these randomized estimates with Clifford gates, you have to invert the final gate to do the prior measurement. It's a little bit hard to scale up and the like. And the other problem is this kind of thing defines that you have Clifford gates here, which you can think of are either 180 or 190 degree rotations, whereas in reality, you're analyzing a circuit that has an arbitrary rotation on average. That's not a Clifford gate. The real physical gates, you try to make them these special gates, but they aren't. And you want to know what's going on and how to improve them. So what we did with the quantum supremacy is we used a new benchmarking called cross-entropy benchmarking, okay? It's similar to randomized benchmarking, but you can measure arbitrary gates, and the answer it gives you is what is the best fit to a model for the particular gate you want. It's a quantum model, and a error is kind of a classical error probability. And this is kind of what you want to know. What gate are you making, best fit, and then how much error you're getting. You can measure purity, which separates out, if you think about the block vector, it separates out if the block, how long the block vector is, which is the clearance, and to whether the block vector is going in the right direction. And this works up to a lot of qubits, easy with 30, up to 50 or so, maybe more with some approximations. And it turns out, which we'll show here, you can predict the performance pretty well with this error probability. And you don't need the amplitudes of the error so much as you see here. Is there any questions at this point?
Let's see. So just going back to your dilution fridge before, are those wires scalable? Will wiring become a bottleneck as the number of qubits increase?
Yes, this is scaled with coaxial wires that you can build commercially, and you can see that that's pretty hard. One of the things I did for the last, let's say 3-4 years at Google, I worked on this very problem, and I kind of thought of a way that you could scale with wires. Unfortunately, I can't talk about it. But I think it's hard, and you know, it's turning this into a high energy physics experiment, but I think it is possible to do that. Mm-hmm. Of course, you have to develop, no one knows, you know, there's no commercial technology there. So the 3 or 4 years was spent figuring out how to do that. Mm-hmm. And of course, you know, one of your constraints is that your wiring system can't cost $1 billion, right? So if you were to scale up to this in some way, it would cost maybe $1 billion. It's about 1,000, you know, let's say to 1 million qubits, it's about $1,000 a channel here. So, you know, we can afford that now, but eventually you want to do something that's cheaper, and there's ways to do that. Mm-hmm. Mm-hmm. And people are working on that. And I have a specific thing in mind. Mm-hmm. So now, you know, as you scale it up, of course, you want to find things to multiplex, which we do already, and that would be great. So, you know, I'm sure in the end, it's going to be some kind of hybrid solution. So just to bring up it's a significant problem.
It is definitely. You had a long list of requirements, systems requirements. What about qubits decoherence time? Is that in there too?
Well, that, if you go back to that, that's a very good question. That really feeds into the threshold number. And actually, you need to, well, that actually comes into the error probability and being better than threshold. So if you want to have 0.1% error probability, then the coherence time of your qubits have to be about 1,000 times longer than your gate times, roughly. So for example, in our qubits, the 1-qubit gates are about 20 nanoseconds, and the coherence time is about 20 microseconds. So it's about a factor of 1,000. And you know, right now it has to be a little bit better than that and whatever, but you know, I would say that ratio, yeah. Now, let's say you have really good coherence time, but your gates take a long time. It's the ratio between that better. And of course, faster gates are always better because you can take more data. So, you know, it's always a ratio between the gate time and the threshold, not just the absolute value of T1. And then, yeah, so you wanna think about that. And then of course, you have to look at the details. So that's not in this, okay? I would say, even if you just told us the threshold as a theorist to an experimentalist, then we can think about what our system is and make it proper.
Mm-hmm. Then you got to error digitization. Is that relevant to surface codes, as in 2 levels as you have there versus higher levels?
Yes, you can think about probabilistically about the occupying excited states. And it turns out that that concept works pretty well. And again, you're just trying to minimize some probability. I'll actually talk about that later. But it turns out that, you know, error digitization kind of works fairly well for that too, because it tends to be an incoherent error.
Mm-hmm. And then just a question about your new testing method. Is it the essence of it that it's used to test the fidelity of an optimized quantum gate?
Yes, that's right. And that's what I was going to talk about next. So that's a good lead-in question, if you don't mind.
As always.
Is how do you do cross-entropy benchmarking? Okay. So this is what you do. You do your basic calibrations, which could be via tomography or other kind of coherence things. There's a variety of ways to do that so that you know the system is basically working. And let's say for a 2-qubit gate, you have some idea of what the gate is doing. Fairly good idea. And this can be simple calibration. It's going to differ for different qubits. But then you want to do a careful measurement of the fidelity and to optimize it. So what we do is we take this fixed gate that we want to know, and then we add to that single qubit gates that are known but randomly chosen, and known and measured from prior experiments that basically use the same techniques only on 1 qubits. And they're easier to calibrate anyway. And then what you just do is run this, and you start off with 0, and you measure at 100,000 times or so what is the probabilities coming out here. What are the probabilities of 0, 0, 0, 1, 1, 0, and 1, 1? Okay. You then take those probabilities, which you've measured with the quantum computer, and then you compare that to the probabilities that you compute with knowing what these randomly chosen gates, you know what the gates are, you have an initial model for what U of theta phi is you just measure what that is. Okay, so you essentially run a physical experiment and run a computer experiment. And then you compare them with this cross-entropy fidelity formula, where you take the X vector of these 2 states and you look up what the probability was that you computed here. You multiply by the total number of output states, which is 4 in this case. You subtract 1. And that gives you a system fidelity, the cross-entropy fidelity. This is the error in your system. And of course, you divide that error divided by m. So what happens is if your quantum computer exactly matches what you simulated classically, that fidelity is 1. If you have bit flips or you have some kind of bit flips, phase flips, errors, this fidelity goes to 0. And then by doing that, you can see how close you are from this to this. And because it's never perfect, you're going to mix some of these measurements with the 0 fidelity, and it's going to be lower than 1. And then what you do in software, you vary theta and phi, and you find the highest fidelity for thetas and phi. And that gives you a new value of these parameters in your model. That's the best fit to the data. And you also get what the error is from that. And this is what you want to know. You want to know, for whatever your physical gates are, what's the most probable unitary for that, the best fit, and you want to know the error. So it's very nice that you can solve this generally. Okay. And so you do that. It turns out you can measure purity, which is the length of the block vector, as well as whether it's in the right direction, which is this, and you can show that helps you do that. So, for example, for example, in this plot, you can take your initial calibration and you measure this cross entropy fidelity versus number of cycles. And this cross entropy fidelity is decayed exponentially. And from that decay rate, you can get an error of about 1%. And then by optimizing this term here, you can show that the optimized gate for what's really going on is about twice as good at 0.62%. Okay. And then you can do some purity measurements, which is more like tomography. You can, again, you don't care what state you end up in the end, you just care about the coherence. It's easy to get that for 2 qubits, it's 0.54%. So what we see is that most of our cross entropy benchmarking error is just from regular decoherence, and about, 20% of it is because somehow our controls are not optimized properly. There's crosstalk, there's other things, and you can benchmark. And it tells you kind of when to stop. Once you get within 10% or so of your optimized, okay, you should move on and fix your coherence. And this just shows that the purity that we measure with tomography or via just cross entropy benchmarking is the same. So it's really measuring the coherence of the system. Okay, so this is a nice measurement. And then what we do is we then do this measurement on all the qubits. And we start by measuring the cross entropy fidelity on 1 qubit, detuning all the other qubits, turning it off, getting an average measurement. And we do it on all the other qubits separately. And then we get this dotted line here, which is basically a histogram, but integrated histogram, which is a little bit better to display the data. And on average, you get about a 0.15% error rate. Now, I told you when running the surface code, we have to run all of the operations in parallel, right, to be efficient and to make sure we're doing things as fast as possible. So you do the same experiment here where all the couplers are all off, but we're doing the benchmarking on individual qubits all simultaneously. And of course, that's more efficient, that's faster, it's what you want to know. When you look at the histogram, it's a little bit worse, but not that much worse. So that means our crosstalk is low and we know how to do things properly, everything's good. Okay, you can do the same thing with 2 qubit errors, and there the difference between isolated and simultaneous is a little bit bigger. They're more sensitive gates, but it's still below 1% on average, and that's good. And then it turns out one of the bigger errors are in readout, and that's been worked on and improved some, but that actually, you only do it once, so that's better, but that has to be worked on. So you can do that. So now from this, you have an error model of each qubit, and that's going to help you with your predictions.
Yes.
Okay, go ahead.
Yeah. So does all this mean that the main advantage of your new method over randomized is the ability to measure error on a non-Clifford gate? And if you were to,
and then of course what you can do if your gate is not a Clifford, but you want a Clifford, you then know what it is, and you can model what's going on with your gates to push it into a Clifford, so that you can very, very accurately state that, because you know what it is and you have a model for how to fix that.
If you were to use your method on a Clifford gate, will you get the same result as the good old randomized?
Yeah, the randomized benchmarking and cross-entropy benchmarking basically give you the same results. And we like conceptually that this finds what the gate really is, and then you know how to optimize it. Whereas, the Clifford gate, it just, tells you what's going on. And then, of course, it's not hard to get the purity information, so you know how much control error you have. So in terms of optimizing the system, this worked very well for this experiment to know what's going on.
Mm-hmm. Does your new method scale just as well as the randomized benchmarking?
So in some sense, it scales better, because in randomizing benchmarking, you have to compute an inversion gate at the end, which can get complicated. And here you just run it from randomly chosen gates and you get whatever you want. It stops scaling at 50 qubits, but then you make lemonade out of lemon and you claim quantum supremacy. Okay, now it turns out that you can do simplifications to do that, but I'm going to say it's really easy to use this up to 30 qubits, and testing patches of 30 qubits with this is enough to know if things are going wrong. So for me, and it's very easy, it's no harder to do 30 qubits than it is to do 2. Okay, it's more computer time, but that's free essentially at 30 qubits. So it's a very effective way to see if it's, because, doing these measurements that tells you 1 and 2 qubit gates and measurement probabilities, but you want to know if you start running many qubits at the same time, will the errors get worse? You don't know that. Simultaneous doesn't tell you that.
Yep.
And actually running the quantum supremacy experiment on many qubits tells you if things are going wrong, which you want to know.
Mm-hmm. Just looking at the 3.8% down there. So so you talked about the readout is done only once, but for the surface code, there's a lot of readout happening on the measure qubits. So would that mean that the 3.8% is a problem after all?
Yes, and what happens is on your 1 and 2 qubit gates, you want to be around 0.1%, and the readout you want to be about 0.5 to 1%. So all of these have to be improved, but I would say the readout turns out to be the most tricky. And the latest data by the Google group really shows that, and I hope to be able to get to that. Okay. Let's move on because there's lots of things to say. So in the quantum supremacy, in the cross-entropy benchmarking, what you're doing is a series of single qubit gates and neighboring 2 qubit gates. And since they're 4 nearest neighbors, you have to cycle around the 4 nearest neighbors. And this is all done in parallel. If you look at a central gate, you can look at the sequence that you're doing. You're basically using random gates as a 90-degree rotation around the x-axis or y-axis, or a 45 degrees in between that. And then you have the neighboring gates, and then you measure that. And then the single qubit gates are about 25 nanoseconds. The control gates here are about 12 nanoseconds. So you can do a lot of gates before you lose coherence, which is about 20 microseconds, because these are so fast. And it turns out that any general algorithm is basically this sequence. okay? It's the simplest sequence. And what we do is we run the quantum supremacy sequence using the simplest sequence by having known calibrated 2-qubit gates and randomly chosen single qubit gates, but known, of course. And so you, like I talked about before, you have a bunch of qubits, you run them through, you get the measurements. What happens is, this is very much like laser speckle, where you take a coherent beam, run it through frosted glass, it diffuses out. Some directions you get constructive interference and bright spots. Some directions you get destructive interference and dim spots. The same thing happens here. Some output bits are brighter, more probability, higher probability, some are less. And then you check that probability distribution by comparing it to a computer simulation, which of course computes which states are brighter and which are not. It's a 1 if it's a perfect match, a 0 in error. It basically, this tells you the probability, this fidelity of having 1 or more errors. If there are no errors, you get a fidelity of 1 for one event. If there are errors, you get a 0. Of course, you have a random mixture of that. And again, system validation, learn control map. This is very nice. Okay, so here's the quantum supremacy experiment. You just do that experiment. You have a full circle in red. You run that on, and in this sense, 12 qubits, a small part of the patch. About 40% of the time, there's no error, so you get a fidelity of about 0.4. And this is a total of about 250 gates. You then increase the size of this, and the probability of an error goes up because there are more qubits, thousands of logic operations. This fidelity goes down, it goes down exponentially. And initially you kind of do this with a laptop and then a workstation, and then in the end, the simulation of 53 qubits, it's 2 to the n states. This has to be done on a big data center, and in fact, you can do this with a small change of the sequence. You then can't use a trick that made this classically verified. The red circles go away because you can't check it anymore. But what you can do over here is make a simplified circuit, say break it into 2 patches of about 25. That you can simulate with a laptop, and then check it. You see it's more or less the same. Since it's more or less the same number of gates, you can check it over here, that's fine. You can do something in between. So this is a good proxy for the red circles, so we expect this to work properly. Okay. And it's hard calculation out here. Now for this talk, this is the important thing here. This black line going through all the data points. This black line is the prediction from gate and measurement errors that I just talked about, for single qubit errors and 2-qubit errors and measurement. And even though this is a way more complex calculation, way more entanglement, whatever, very complex, we can predict it from these measurements. This is amazing. I didn't know if this would be true, but this you can do. So I'm just going to talk about that. Is first of all, the full patch elided. It's a different amount of computational complexity. It's a different amount of entanglement, but the prediction is all the same. So the error of a complex system does not depend on the degree of complexity of the calculation. In fact, the fidelity is just given by the individual fidelity of all the operations. This is classical physics. Okay, this is high school physics, right? You find the probability, multiply it. And this is what's assumed with error correction, and it's good to see that that happens. So quantum mechanics works on a big Hilbert space. And finally, I want to say we can test the model of digitized errors. Out of, in this case, I think it was 14 qubits, and you have about maybe 500 gates or so, 500 gates. I choose one of the gates in there, okay? And in the simulation, I add in a continuous rotation of the state so that theta equal pi is a phase shift. And what this shows is that with no error in the system, you've got a fidelity as expected, but you put in a phase flip operation, the fidelity goes to 0, as I said it did, okay? So a phase flip loses the coherence. But what's interesting is if you do a continuous amount of rotation, you get the data that goes down in this, this cosine way, and is very well fit by this error digitization model of x cosine squared of theta over 2. So you see that even though this is in the middle of a complex calculation, this digitization model of errors, where part of the time there's no error and part of the time the error, that's what this formula is saying, works for a operation in the middle of some complex circuit, you know, of course, in this particular circuit. And that's nice. It's kind of the reason why, you know, the fact that the physics works this way is part of the reason why the fidelity can be estimated in a simple way. Okay. So why are there no additional errors? It's first of all a low crosstalk design, doing that for a long time. These square root of naught operations actually are effectively over many operations doing spin echo or a dynamically decoherence. It's basically an incoherent version of that. And that decorrelates noise, especially drifts in the qubit frequency. And basically, there's small noise, correlated noise in time, but this actively decorrelates it. And I'm going to say that if you have a general purpose algorithm, not what we did here, you can add square root of naught and naught gates to the algorithm. It's basically a gauge transformation. You still know what the answer is, basically adding echoes and making it work properly. So there's a lot of experimental tricks you can play to make this work properly. In fact, when you do the surface code, you do things like that to get it to work better. So, you know, and this is, again, well known that this works. So that's part of the tricks that we do.
What's the wall clock time to run your method there and for Google Sycamore?
So the time for each sequence is about 10 microseconds or so, a few microseconds. Mm-hmm. And then it takes about 200 seconds. I think it was a million samples for a few minutes. And then in the latest case, that would take thousands and thousands a year to check on a classical supercomputer. So, you know, it doesn't take too long to get a lot of statistics. Okay, let me go on. I have 20 minutes, and I really want to get on to the last experiment, which is error correction experiments. There's been a long history here, people checking things different ways. And what I would say is the latest experiment done by Google, put on the archive in February, gives you kind of, I think, the latest version of how well the surface code works and gives you a lot of information that's going on. So it's exponential suppression or bit or phase flip errors with repetitive error correction. This is the initial kind of the 2-qubit example in an array that I gave in the beginning of the talk. So what we do is we take what was done was that you take this large array and you define a linear array of qubits to do this repetition code, where you're either correcting for bit flips or phase flips in separate experiments. Okay, so it's a 1D chain. I'll talk about a more complicated thing later. And then in terms of the control Z gates, which I told about previously in terms of a homework problem, to do a bit flip, or excuse me, to do a phase stabilization, what you do is you create a data states that are either plus or minus, they're eigenstates in the phase basis. And then you do a Hadamard to convert that into a bit. And then you do use the control Z's to do the parity, kind of as we did before. So then after you take the measure qubits, you do the parity, you then measure it. And then the new thing here is you reset it into the 0 state for the next thing. And given that this is fairly fast and this is fairly short, and there's some measurement crosstalk, we do a bunch of X and Y gates to do this spin echo dynamically decoupling, which I just talked about, in order to decorrelate and reduce some errors. Okay, and as I was talking about previously. And then you do this a bunch of times, like I was talking about, and then to know if you had a logical errors, you do a measurement of this state at the end. And then you're basically running the surface code in one dimension to see if things are working. Okay. Now, this is a very important diagram to say what kind of data you get. You want to visualize your data. So this is the case of 5 qubits with 4 measurements in between. And this is t equals 0, round 1. Okay. And what you do is each round you measure if the qubit state changed. Okay. Now, and you have to do a special things for the beginning and the end. It's in the paper. It's too complicated to talk here. But normally you expect that once you measure what the parity is, and what you should know since it was given initially, you see if it hasn't changed. And you see from going from this to this, the black dot means you got the exact same output out of all your measurement qubits. Okay, so there was no error going from here to here that you can measure. Then going in round 2, what happened is this value, say it was 0, this went to a 1, and this value, say it was 1, went to a 0. And you see it in a pair, okay? And when it's a pair, we mark this as a blue line, and this is an error, a pair that's in space. So this is kind of like the data qubit error that I was talking about it before. Now, you can also get errors that are both in time, which are measurement errors, as I talked before. The measurement changed, and then it changed back, okay? But because of this code, you can also have this pair in space differ in a pair in space and time. So then you have a pair of errors between here and here. And you can see that in here. Let's say you have an error that happens right at this point. Well, in terms of measuring in this neighbor, it's going to have an unerrored state. But in terms of this is going to show up as an error here. So because of the sequential nature of you do it, besides just space and time, you can get a space-time. So that's what the gray bars represent. And then on the edge, you have a pair, but it's matched to the edge where there's not actually a measurement, but you can have a boundary qubit error too. So this is a nice way to describe when you take the data in a very simple graphical model where your errors are. Any questions on that?
Just somebody remarked that this exact picture that you have on the left, that was the kind of thing Austin had on his homework yesterday, which I was part of working on. It's great. It's now his homework makes total sense.
That's great. Thank you. That's great. I'm glad he did that. And then the picture on the right is how to kind of visualize that. Now, what you do next is you say, what's the probability of, by doing the experiment 100,000 times, what's the probability to see a red dot at a certain round and a certain qubit? And then you plot that in here in the gray bars with the different qubits versus the different rounds. So it's different rounds, different gray bars here. And then you average all the gray lines to get an average rate over the whole system. Now, what happens is you tend to get lower errors in the initial and final round because it's a simpler thing. And then what's nice is you see that the error per round is actually pretty flat. Okay, so there's nothing going on getting worse at time. And then there's, and then there's a little bit, few differences between the qubits. But it's a way to kind of do an initial check of how your system is. You also get a magnitude of the detection events. I mean, this is from any error. It's the whole cycle, and you get an idea of how good that is. Okay. Now, given that you have errors that occur in pairs, what you really want to do next is analyze the correlation of these errors occurring in pairs. Okay, and that's what I show in the next slide. Okay, and what happens is these X's are 0 if there was no change in the detection event, or 1 if there is a change. And you're getting a correlation matrix, which is basically looking at the correlation of a pair of errors. And then, kind of normalizing it and comparing it to what you expect if it's just randomly occurring, which is, for example, this, and this is a normalization. So this is basically a normalized correlation errors. Now, when you look at these errors, you have errors that are that have versus numbers, and errors that and rounds in terms of qubits. So if we're going to have a 2D plot, it's going to be a little bit complicated because we have to put all of this data on a 2D array on a 1D line. And what we're going to do is order it either in the minor axis being the rounds and the major axis being the qubits, or we're going to order it this way. I have 2 plots here because it'll show different things. This is very nice in this paper by the Google group. So here you have the node index so that the time is the fine ordering. And then this is for I and this is J, and the color intensity here tells you what Pij is. And what you see here is 3 main, so first of all, it's symmetric from one side or the other. So just look at this one side. In the thing here at the edge, these are correlated over time. So these are the time pair edges, okay? And then if you look at these 2 here, these are separated by 1 qubit, okay? So these are the space oriented. And what you don't see, you have to blow this up. These are 2 actually parallel lines where one line here is space-time and one times is space. One is separated by 1 time unit. So it basically shows that, yeah, the majority of errors are what you expect. Now you can do the same thing on this slide, and here it's the space is first ordering, and then the time is the big edge here, and you display different things. In the beginning, you see the space, and space, time, and time is on the outer edge here, and the space is on the inner edge. And you can see that things are, anyway, you can blow up and see that. So this is good, and that's the major errors. That's what we expected. But what's very nice about this is you can really dive in and check whether the thing is working properly. So for example, you see some faint low probability events over here. And let's look at this. This is an event between qubit 3 and qubit 7. Like, why is there crosstalk between qubit 3 and qubit 7? Because they're separated on the line. If you go back to the diagram here, you see qubit 3 and qubit 7 are actually next to each other because the line is wrapped around. And so it's not unexpected to get a little bit more crosstalk there. And it tells you in the future, you either have to decide whether that crosstalk is low enough to be okay, or you have to work on your design of the qubits to make it small. It's a pretty small number, but there is some crosstalk there, okay? There's some examples here where you see there's a bunch of errors out here that expanding out in time on qubit 2. Okay, this actually is leakage to the 2 state, which I hope to get to in a few minutes. You can look over here and you see there's parallel lines over here that gets displayed. This is major, this time index. This says that there's some correlations over most of the qubits from this time to, let's say, 2 cycles or 3 cycles or 4 cycles. And there's some correlated errors going on there. And again, it tells you have to go in and try to understand that. So this is a very nice way to really go in and figure out what's going on and to measure the magnitudes, okay? And for example, for the space edges and the time pairs and the space-time pairs, you can measure that versus different qubits, and each of these versus time. Try to understand what's going on, compare it to your model, can do it for the other ones, and really get a detailed description of what's going on and of course, how to fix it. Okay. Any questions on that?
There's a general question about, there's something confusing about having a digital error model where the continuous errors are collapsed to digital errors via measurement. And then you have this notion that your benchmarking method decreases continuously. And so the question is the reconciliation between these that this exp't thing that you had is a statistical quantity that is averaged over many runs of the circuit?
That's correct.
Aha.
100,000 or 1 million runs. Now, what's nice, and that's a good way to check that the model is working right. What's nice about the surface code is you're getting detailed information from every run. Each run is different than this. Okay, this is an average over many runs, but this is a single one. And by looking at the correlations, as I just showed you, you can see if there are any single run correlations going on here. Of course, you have to do some statistical thing, I guess, but you can get more information. And the fact that you're doing error correction kind of tells you when you want to have an error corrected machine and you have low errors, there are ways to kind of understand what's going on and measure the errors. And of course, that's how you're going to correct it.
If you got faster 2-qubit gates, would that directly translate to a lower qubit error rate?
Yes, so that's in one of the next slides, okay?
As always.
And let me get to that, okay? Because I'm running out of time and I want to get to that. So one of the things you can do before I get to that is that states do lead to 2-state leakage in errors. So for example, normally what happens if you look at the data qubits and you run it a bunch of rounds, you get, let's say, 1 or 1.5% errors versus the number of rounds, because you continually leak into that state. And this makes the error correction worse and worse over time. It's a real problem. The nice thing you can do is you can actually reset the measure qubits with a certain protocol I've given here, where you swap that 2-state excitation of the qubit into your measurement resonator, and then you hold that for a certain amount of time, which is going to leak out the state quickly, and then return and get rid of that. So we use the measure qubits also to remove the entropy of the system. And with that reset, the measure qubits basically are very low, and the data qubits, which are only indirectly reset, go down to some value that's a little bit reasonable. You probably have to fix that in the future. So for example, on the reset data that I showed previously, if you don't, this is with the reset, if you don't do the reset, you have really bad leakage errors all around here. And now most of the qubits got fixed, and there's a little bit wrong with this one that has to get fixed. So again, it's nice that you can identify those errors. Now, what you then do is decode the pairs of these errors, as I talked about, and that's using minimum weight matching. I imagine Austin talked about that. And then you look at the number of syndrome rounds, and you basically find the logical error increases linearly with the syndrome rounds on this log plot. It's this curve. And then what you do is you look at different code distances from 3 to 11, and the logical errors go down as you go to 3 and 11, and it's going down exponentially. On a log plot, it's a constant offset there, which is what you want. And you see the offset at 50 rounds is 10 to the minus 3 for your logical error. So you've done things quite well. And also, if you look at the logical error per round, you can show versus the code distance, you can show that starts out at about 10 to the minus 2. And then over time, that gets better and better, and you get 10 to the minus 4. And that's fine. And then there's different values for the phase flip and the bit flip. Okay, so that you see here. And here's again the formula I showed before. This is a measurement of the lambda. It's about 3.5, and that's pretty good. Okay. So finally, to get to basically the last slide is going to your question is, what's the error budget? So what you can do is you can measure lambda, as we just did in this complex algorithm. And then from basically the kind of measurements I showed in the quantum supremacy experiment and others, you can write an error budget for what's going on. And you see here for the error budget, the control Z's are the red, and the measurement and reset is the orange, and the idle is really small. But what happens is, because of the very long time of 900 nanoseconds, there's a relatively large error due to the 900 nanosecond delay, even though you use dynamic decoupling to that. And basically, you're dominated by the long measurement time and the qubits decaying from that. And on top of that is some extra error that's not included in the model. And you see it's there, but it's not a huge amount. It's some percentage of that. And you can really understand what's going on through the basic design. And these are probably due to these other correlations that you see. Now, that's great, and you explained that. Now, what you really want to do in the end is look forward to the full 2D model of the surface code. And the Google group is working on that, building a surface code with 54 or more qubits to do a distance surface code where you can compare both the first order errors and second order errors to kind of see do a measurement of this lambda factor. Now that's kind of the next thing they want to do now that they get this to work. But in order to understand that experiment and project what it may do, what they did is a simplified version of the surface code where you have data qubits here, and you do this is an X, or this is, I think this is a Z measurement of these two. No, this is an X measurement between these four, and then we do Z measurements between these two separate here. And this is a surface code where you actually can't correct for your errors, but you can measure the errors and then check the result at the end to see if you measured right, and see, for example, if you have no errors during the entire run, what fractions do you keep? And when you do that, it's very similar to what we've seen here. If you look both at the X data and the Z data, you see the fraction of the runs that are kept are going down as you increase the number of rounds. And what's very nice is if you just take the model from here and project it for what's going to happen when you do this, you get the following projection. And that projection basically follows what we see with the data, and you would have to include very small amount of stray error. So basically, it says that when you run a two-dimensional surface code, a proper surface code, things are going to work according to projection. Now, of course, when you look at this, you see that lambda is less than 1. So you want to make it better. And it says that the major part of this is improving what's going on when you're doing measurement and you're effectively idling the qubits, and you want to fix that. Although it's clear you want to improve the control Z. And given that, you kind of know what to do next in terms of making things better. But it shows that you can at least do a decent experiment and show how that works. And it kind of shows the kind of data you're going to take to test whether you're doing error correction properly. And I think this is a very good kind of mock-up for what's going to happen. So I think what is it? It's 3.5 hours. I'm gone over time. Thank you for letting me to go over a little bit. Before just one more slide. All these experiments are very complex and takes a big team. And it was great working for Google up till last year, and really worked with a lot of talented people who know how to get experiments to work. And it's really great to have worked with this team. And I wish them the best of results, as you've seen here, for the future. So now let's go back to the questions. And I wanted to make sure I didn't forget that, because that's the key part of this.
Oh, amazing, amazing talk. Okay, there are some questions. There are also some questions that I didn't ask along the way. So if you don't mind, I will ask. So while we are on this slide, just say one more time, the left picture and on the x-axis you have repetition Z, repetition X, surface. What is it again? It means
the repetition Z is just the bit flip, single line. So it's just this experiment here, where we have a single line of qubits, and we run what's called the repetition code to test that, either as a bit flip test or as a phase flip test. These things change a little bit whether you're doing bit flip or not. And then the surface code was this small distance to surface code of 7 qubits, where you're just looking not at error correction, but also error detection. Okay.
Are there any of these challenges with surface codes that could be solved in the compiler instead?
I think people kind of have simplified that code enough, in a large extent. So I would say, for example, one of the compilation things you can do is whether you're going to use C-naughts or whether you're going to do control Zs, because both of those are possible. People are looking at that. And, you could say in the end, they're both the same. What's nice about the control Z case, which is, what we have here with the control Zs, is that when you look at the control Z interaction, the control Z interaction is independent of the phase of each of the qubits. Okay? And what that means is when you're worried about stabilizing the phase of a qubit over time, you only have to worry about the phase of the microwave generators and the phase of that one qubit. The phases we don't have to worry about the phase of each qubit. Okay, you just stabilize them independently. When you do the control not, all of your microwave signals have to be synced together in phase and the whole system has to be synced together in phase. So that makes the CZ a little bit easier to implement experimentally.
Do you have that directly on?
Cheaper.
Do you have that gate directly on Sycamore, or do you have to?
The control Z is an intrinsic gate in the Sycamore that you can do. And I didn't get into the gate design. Yeah. You can either do, there's several gates you can do, but that's something intrinsically. And we've been working on the control Z gate for a decade or so.
Yeah.
So that's something you know how to do and calibrate.
There's a question in a different dimension. What classes are you going to teach when you return to Santa Barbara?
What am I what?
What classes are you going to teach when you return to Santa Barbara?
Oh, I don't know yet. I'm
Oh.
still trying to recover and figure out what I'm going to do.
Did you teach classes in all these years here? You were engaged?
Oh yeah, before I moved to Google, I was teaching classes. I taught electronics and lab course for many years because that's obviously where my expertise is. But I did enjoy teaching other courses too. And I've enjoyed very much teaching this course kind of at a graduate level. This is quite nice.
Oh, there are bunches of other questions. There's one high-level one that I think goes way back in the talk. So the error syndromes are not unique for these surface codes. Why is this not a problem?
I have dropped from my vocabulary of error correction the word syndrome.
Okay.
So can you just to make sure that I see when I hear error syndrome, I don't know what that means from the vocabulary. I know that people know what that means, and I should know what it means. I'm sorry, I've forgotten what that means.
I think that it roughly means this product that ends up being -1 or 1 when you focus.
Oh yes, yes, okay. So the error syndromes is these parity measurements.
Yeah. So
okay,
so
I treat them as parity measurements. Sorry.
That's great.
Okay.
That's maybe a better terminology. I should learn that. But they are not unique, are they?
Well, each parity is a separate number. So all of these different measure qubits will give you different zeros and ones. Okay, it's different, and you need all that information of the 40 or more measurements to know what's going on. So you have a huge amount of information there that you're extracting from the measurement.
So here's a different question. So we have the Gottesman-Nil theorem that talks about simulating just Clifford gates. Would it be possible to use some kind of trick there to maybe have a classical subroutine as part of the whole picture that compute with the stabilizers, and then maybe that way improve everything?
Yeah, so the question is, I think the question is, could you change these kind of things to make your Clifford gates better? Is that a good way to?
So that's possible. I think that the part of the question, as I understand it, also has to do with whether one could bring in a classical computer to do something there as part of the.
Well, it turns out that the classical computer corrects for the bit flip and phase flip errors. So that's already included here. And you don't have to feed back to the bit flip and phase flip. When you do the logical operations, so X and Z is done in the computer. When you do the single qubit logical operations, there are some physical changes you have to do with the gate, and as well as with the non-Clifford gate. So there's a mixture. And of course, if you could add some feature to this that made this either to be easier to make or do it in software, that would be great. And I would say that's really important piece of research. Of course, if you make more complicated connections and more complicated measurements to do that, and you lower the threshold, then it might not be a net win. So again, that's the thing to do for a system, is to do that. I think for the color code, for example, this operation I think might be easier, but the color code has a lower threshold. and then you have to see whether you're winning in the end. And then you have to think about, you know, your various distillation. So that's a very complex optimization problem. And I think it's good people are thinking about it and fixing it, but they have to make sure that when they fix one thing, that they aren't making something else really worse. And I would say the nice thing about the surface code, which I like as an example, is it gives you an existence proof, and that you can kind of, for one concrete model, kind of understand what all the global constraints are.
Mm-hmm. Mm-hmm. We have some questions about correlated errors. So you mentioned that the quantum supremacy result indicates that fidelity was the product of individual gate fidelities. Right. So does that mean that correlated errors are not so important?
I think, yes. And I think it indicates that for at least, you know, when we design the chip and the experiment properly, that's not a huge problem. More or less that it's predictive and correlator. But the problem with the quantum supremacy experiment is whether you get one error or two errors, it gives you the same signal, okay? So if an error comes in pairs, because it's correlated in some way, you won't know about that, okay? So you know, the fact that it matches means it's pretty good, but you aren't sure. However, when you look at the Pij matrix, and you look at these error rates here, correlated errors are going to give you a problem, and you're not going to keep going down exponentially. So it's the error correction experiment where you really get to see the correlated errors in more detail. And I'm going to say these kind of experiments, like this Pij experiment, is probably part of the thing, the suite of tools you're going to use to look at data to see if they're correlated errors. And, you know, for example, when you see correlated errors, what's going to happen is this is going to go down, and at some distance, it's not going to go down anymore because your correlated errors are dominating you. Mm-hmm. And then from the Pij, you're gonna try to figure out, well, what exactly is going wrong. Mm-hmm. So these are the kind of tools. And the nice thing is, I think with the surface code, you can to some degree kind of show that the system is working right. You can self-check it, and there's tools to look inside of what's going on. But it's really these surface code experiments that's going to tell you that.
So you talked about correlated leakage errors, and you talked about cosmic rays. Are there other experimental studies that should be done on correlated errors in this context of quantum error correction?
You know, I think it's just a matter of people building more complex systems and taking this data and looking for these correlated errors. You know, it's kind of interesting in terms of the cosmic rays, because there have been quite a few experiments on this so far, but, you know, some of the conclusions have been, well, the T1 is degraded by a few percent on average, okay? So when you look at an average effect doing this, it looks very bad, but when you actually look at these experiments to do at this, you then see the correlated errors. And one of the reasons you knew that there are correlated errors is people have been making low temperature detectors and from superconducting devices, and they've seen these kind of errors. So it's something you can expect. But, you know, for example, at low temperature, it's well known that you have two-level states, excited states trapped in the crystal, and they slowly decay over time. That's going to inject energy in the system, not as much as with cosmic rays. And then you have to maybe fix for those, as an example. So I think it's more of something that you have to be looking for. And I think what's going to happen is, now that people are doing more complicated surface code experiments, those kind of results will become more apparent, and then we'll know how to fix. But those will represent more constraints on system design, and you just have to take the data to see those.
So going back to this thing with that surface codes requires 4 nearest neighbors. So IBM seems to be different. Is surface code a good fit for the IBM architecture? And if not, they must be using something else, right? What are they using?
So I am not an expert on that. I had an email exchange with Austin Fowler, and he would be the person to describe that. But what I understood is that the IBM is using a different connection diagram. And if you have, let's say, right now they have at most 3 connections, and there are some 2 connection nearest neighbors. And my understanding is, although you can do some check experiments, this is not scalable to a super low error rate. Okay, so it's fine for now. I mean, it's hard to connect the 4 nearest neighbors. That's right. Now, if you have about some 3 connections, I think it's 3, maybe it's 2, and then some 4 connections, you can then basically do the surface code. It's enough surface code like, but then the threshold gets worse. Okay, so it's a question of trading off threshold for the amount of nearest neighbors. And it's great that they're checking it. I'm sure they'll do experiments. But my guess, looking at this, is you're going to want to go to the 4 nearest neighbors because you can build it, and it's efficient, and and you just have to solve all the problems of the nearest neighbor errors that you get. Okay.
Very nice.
In some sense, what was nice about our experiment, where we have a wire going in to the coupler between the qubits, is we can turn on and off the interactions and make sure that we don't have nearest neighbor problems as much, contributing big errors. But again, that's an architecture issue that'll have to be worked out.
So here's another question. So you talked about spam fidelity at some point. Suppose the spam fidelity was really good, higher than the 1 qubit gate fidelity, higher than the 2 qubit gate fidelity. Would you do your benchmarking differently?
I didn't get there was some Ben fidelity. I didn't understand the fidelity.
The spam fidelity.
The spam.
Yeah, the spam fidelity. So suppose it was really, really good. Would you then do benchmarking differently?
That's a good question. I think, the problem is, yeah, it would certainly help you with tomography. I would say it's hard to get these spam errors very low. So it's hard. But I think, that would be a good question. The nice thing is when you do the multiple gates repeated, you can amplify that error just by doing more and more gates. So if you have 10 to the minus 6 error, you do 10 to the 5 gates and you see what happens. And what happens is, maybe I would say this. What's nice is you want to know, if you do 1 gate, what the error is. But you want to make sure that if you start piling up gates one time after the other, whether things degrade. So doing it with randomized benchmarking or XEB is kind of more realistic, because you have to do a sequence of gates anyway, right? So just doing tomography on 1 gate, it's nice, but it's kind of this academic gate. It's not what you're going to be doing. It's nice to know what the answer is. But in the end, you want to know what happens when you do a lot of gates, both in time and then also in space too, which is why you want to do simultaneous. So I would say, doing it this way and measuring it versus time or versus space is really useful, because it tells you that things are going wrong. I think it's more important to check for crosstalk, both in time and space, than it is to get all this phase information from tomography. I mean, maybe that'll help you, but if you have some weird crosstalk, it's more information, the better. But more techniques, the better. But I would say you get quite far with the RB and the XEB measures.
Mm-hmm, mm-hmm. That's a different question. Would it be possible to combine defect-based and planar-based surface codes into a single architecture?
Defect-based or planar?
Planar-based.
Oh, the planar would be just what I talked about originally, and defect would be the holes.
Yeah.
Yeah, so what's going to happen is the field will start with the planar base because we have to scale up the number of qubits, and we have to understand that. And then as soon as you want to do logical operations, I mean, in a realistic way, I mean, you might be able to do it other ways, but in a realistic way, then it seems like you'll go to you'll introduce the holes. Now, you know, this is probably a good question to ask the theorist because I haven't thought that much ahead. Mostly I've thought ahead that, you know, what hardware do you have to build? And in either case, you have to build a big 2D grid of qubits, you know, that you can control and turn measurement on and off. So, okay, you know, that's what we need to do.
Do you have an opinion about other codes, such as the bosonic code? Do they have a chance of becoming better than surface codes?
So I know you're talking about a bosonic code yesterday, and I think it's very interesting. What's interesting about the bosonic code is that it's a way to reduce the number of physical qubits to do to a logical qubit. But I hear that the latest implementation is that you do the bosonic qubits, essentially make the qubits better, and then you build a surface code on top of that, you know, to take advantage of that. So in my knowledge, it's a combination, but I'm not, you know, I'm not involved enough in that to know for sure. The one thing that that one, of course, has to be careful of is that in the bosonic codes, you have longer coherence times, but the essential gate operations are longer too, because it's do a coding. So the reason why all the results here work so well is because the group has worked very hard to make very short single qubit gates, and even make the 2 qubit gates, which are typically hundreds of nanoseconds, to make that 12 nanoseconds, to make it really fast. So I would say the strategy here has been, of course, it's the ratio of the coherence time, the gate time, if that matters. So make the gate time really short. And I think that's why, you know, for many years, figuring out the architecture and the way you do that, that's worked. So for the bosonic codes, I have not sat down and thought about what effectively that ratio means. And, you know, how would you go about doing that? And again, that's something that you need to talk about, you know, more carefully. I would say my system integration slide didn't include that kind of complexity, and that needs to be addressed.
There's a question going a ways back about your correction for phase errors. Is that one doing something similar to the phase-locked loop in electrical signal processing?
Yeah, thanks for someone catching that. That is kind of the picture I have in my mind, is that you have to put in kind of a phase lock loop, and that the error correction in Z is locking the clock together to your experiment. So that phase of the qubit can drift a little bit, and then the error correction effectively brings that back, you know, into phase lock in a digitized manner, in a strange manner. So yes, that's in fact, I would use that language to electrical engineers. Okay. But this is physics talk, so but thank you that someone thought that. That's exactly what I like about that picture.
We have a broad audience here. So would you be willing to say an opinion about whether silicon spin qubits can meet your long list of requirements in in the somewhat short term?
So, you know, all of the qubits have their pros and cons, and you know, it's hard to talk about that because, you know, next month someone could come out with the silicon qubit where they have super high fidelity, say on a 2-qubit gate, and then that completely changes the architecture or way you would think about that. So, so that's good. So, you know, my statement is well, let me just say this in general, and I'll get back to silicon qubits. When you write something down on paper, every qubit type looks pretty good. And what happens is you start taking data and you start seeing what all the deep dirt physics that nature is giving you, and then it starts getting harder and harder. Okay, and this is what's difficult. And in the first thing you need to do is you need to have data on qubits to see what the problems are. And then what you have to do is you have to start building, let's say 5-qubit system or 10-qubit systems or 50-qubit systems to know what happens when you scale and know all the system engineering constraints. So what I would say is when you went from 1 or 2 qubits to 5 and 9, which is what we did, that taught us a lot about system issues. And from that, we would know how to make the Sycamore device at 50. At 50, you're really understanding quite a lot about how to scale up, because you know you just scale up by making that bigger, and you know what all the constraints are, and you know all the design rules that you have to do. So at that point, it's even harder to figure that out, but you know what's going on. So for example, at the silicon qubits right now, they're going from 1 or 2, and they're designing up to 5 or 9 or 5 or 10 or whatever, and that's a really good stage, and they're learning about that. And you just need to see what people are doing to know what all the practical constraints are. And then, you know, my statement is someone can make not just 1 or 2 qubit, but you can make a 5 or 10 qubit system. It's a simplified system, but they have very low error rates, 10 to the minus 4, 10 to the minus 5, save for CZ, very low measurements, so that you can make a very accurate qubit. Then that's a really interesting system, okay? So I'm not sure that it's physically possible, but you know, okay, people are clever and we'll have to see what happens. The one thing about silicon qubits that concerns me, for example, is they're so small. If you look at our qubits, they're almost millimeter size, and that allows us to get our wires in to control them. When these qubits are some micron size, you have all these gates, there's a lot of gates and a lot of wires coming in, you know, how will that scale? And people have ideas on that. But those ideas add a lot of complexity to the system. Now, of course, it's silicon, and maybe you can build CMOS control, and that's really great. So we have to see what happens. But you know, people have to keep working on that and showing that things work. So it's good. It's very good that there are all these different approaches. And then, you know, we'll see in the end, when you think about systems, what are the important things to do?